Welcome, curious minds and sleepy thinkers. You found a soft place to land, a quiet corner where the whispers of the cosmos can drift gently into your awareness, a space where the questions are vast and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight we're going to tiptoe into one of the most profound inquiries ever conceived, one that invites us to stretch our imaginations across unimaginable distances and back through the very fabric of time itself. It's a journey not through the bustling halls of scientific equations, but rather a quiet stroll through the universe's most tender secrets. Our companion on this journey is a magnificent creation, a marvel of human ingenuity and unwavering patience. It's known as the James Webb Space Telescope, or JWST, a name that echoes through the annals of space exploration. A tribute to a figure who once guided our very first steps onto the lunar dust. This isn't just a machine. It is, in a profound sense, humanity's newest, clearest eye, designed to gaze into the deepest, most ancient parts of the night sky. Imagine for a moment an instrument so exquisitely crafted that it can catch the faintest glimmer of light that has traveled for billions of years, a light that holds the story of creation itself within its shimmering threads. But why, you might softly ask, would we pour so much effort, so much ingenuity, so many decades of tireless work and billions upon billions of dollars into building something so intricate, so delicate, yet destined to exist for a relatively fleeting span of perhaps 10 years in the cold embrace of space? Is it simply a testament to our insatiable curiosity? Or is there something more, a deeper calling that compels us to reach out into the silent void? This is the central whisper we will gently explore tonight. The answer, as it turns out, is not merely about seeing further, but about seeing backwards. It is about reaching across the vast ocean of time, pulling back the cosmic curtain, and glimpsing the very first flickers of light that ignited after the universe began its grand, expansive dance. So let your thoughts drift. This isn't a race through complex theories or a strenuous effort to grasp every single detail. Instead, it's like floating through a galaxy of ideas, each star, a question, each nebula, a mystery, all while cradled in the comforting warmth of a cup of chamomile tea. We'll wander through the science and the engineering, not as a lecture, but as an unfolding story acknowledging the many challenges and the sheer perseverance that brought this incredible spacecraft to life. Because truly, this is a tool unlike any other, promising to unlock clues to the universe's very origins, revealing secrets whispered across eons. Imagine, if you will, being on the shore of an endless dark ocean. The waves that lap at your feet began their journey unimaginably far away in a time long past. Some waves are fresh, carrying the scent of recent storms, but others are ancient, the ripples of events that happened so long ago that their beginnings are almost lost to memory. The James Webb Space Telescope is in essence our most sensitive sensor. Dipped into this cosmic ocean, not just feeling the gentle swell of recent waves, but attuning itself to the faintest, most distant tremors, the very first ripples that spread out from the dawn of creation. It's an attempt to feel the original splash, to understand the very first movement in this grand unfolding cosmic ballet. The human spirit at its core is a seeker. We look at the stars, not just as distant points of light, but as beacons of knowledge, as storytellers of cosmic narratives. For centuries, our telescopes have been our eyes extending our reach, showing us wonders we could never have dreamed of. From Galileo's first crude spyglass revealing the moons of Jupiter, to the mighty Hubble painting breathtaking portraits of galaxies and nebulae, each instrument has been a step further into the unknown. But the universe, in its infinite complexity, always holds more. It beckons us, teases us with hidden layers, with whispers of a time so profound, so utterly fundamental, that our current vision simply falls short. And so the concept of a next-generation space telescope began to stir. It wasn't a sudden flash of inspiration, but a slow, persistent hum in the minds of scientists, a growing awareness that to truly understand our place, our origins, we needed to see beyond the visible, beyond the familiar. We needed an instrument that could not just observe the universe as it is now, but as it was. Think of it like a cosmic archaeologist digging through layers of time, carefully unearthing artifacts of the universe's youth. Each layer reveals a bit more, each fossil tells a tale, and the deeper we go, the more fundamental the story becomes. The sheer scale of this ambition is staggering. For 25 years, teams of brilliant minds from across nations and disciplines have dedicated their lives to this single audacious goal. It's a testament to patience, to perseverance, to the belief that some answers are so vital, so enriching to the human spirit that no effort is too great, no challenge too daunting. There were moments as the years stretched into decades when the dream of the James Webb Space Telescope seemed to waver, when the practicalities of engineering, the immense financial commitments, and the relentless march of time threatened to extinguish its light before it ever had a chance to ignite among the stars. It was like watching a delicate seedling try to push through concrete, needing constant care, protection, and belief to survive. Yet it persevered. Through redesigns that reshaped its very essence, through budget debates that tested the resolve of nations, through engineering hurdles that seemed insurmountable, the vision held firm. It was a collective act of faith, a shared commitment to unraveling the universe's deepest secrets. And as it now floats in the inky blackness, a silent sentinel gazing backward through the cosmic expanse, its very existence is a triumph, not just of technology, but of the human spirit's enduring quest for knowledge. Consider the immense tapestry of scientific endeavor. Each thread is a question, each knot a discovery, and the James Webb Space Telescope is like a new, incredibly fine needle, capable of weaving entirely new patterns into this tapestry, patterns that reveal the very earliest threads of existence. It is poised to show us the universe as a newborn, perhaps even a universe still in the process of being born. What could be more profoundly beautiful, more deeply captivating than to witness even indirectly the first moments of everything? This evening, as we drift through these thoughts, remember that the universe is not just a collection of distant objects. It is a story. And the James Webb Space Telescope is our intrepid storyteller, whispering tales from time's long past, tales that promise to deepen our understanding of who we are, where we come from, and the magnificent, awe-inspiring journey we are all a part of. Close your eyes if you wish, and let the gentle hum of cosmic wonder lull you into a state of quiet contemplation. The universe is waiting to share its secrets, and we are here ready to listen. Let us now gently drift back to the seeds of this colossal dream, to the very first stirrings of an idea that would blossom into the James Webb Space Telescope. The story truly begins in the quiet halls of NASA sometime around 1996, where minds steeped in the mysteries of the universe found themselves pondering the next great leap. For years, the scientific community had basked in the glorious light of the Hubble Space Telescope. Hubble, launched in 1990, had been nothing short of revolutionary. It had unveiled breathtaking nebulae, charted the expansion rate of the universe, and peered into galaxies so distant they were once mere smudges of light. It was undoubtedly a colossal success, a testament to human ingenuity reaching for the stars. But even as Hubble continued to deliver its stunning portraits of the cosmos, the most ambitious dreamers, those who dared to ask, "What's next?" began to feel a subtle, insistent pull towards the unseen. Hubble, for all its might, primarily observed the universe in visible light, the spectrum our own eyes perceive, and in ultraviolet light. It had some infrared capability, yes, but it was like trying to hear a whispered secret across a vast, noisy auditorium. To truly understand the universe's most profound secrets, to hear the very first faint whispers of creation, a different kind of ear was needed. Imagine standing in a grand ancient library filled with countless books. Hubble was like a brilliant scholar meticulously reading every word in the visible sections, understanding the stories of the middle and later chapters of the universe. But there were entire sections bound in deep unlit corners that remained unread. These were the infrared sections, volumes written in a light invisible to our conventional eyes. The scientists realized that to truly complete the cosmic story, to delve into the primordial chapters, they needed a special kind of lantern, one that could illuminate these hidden pages. This realization was the quiet genesis of what they then called the Next Generation Space Telescope, or NGST. The initial vision was, by today's standards, almost quaint in its modesty. The plan was to craft an 8-meter aperture telescope, a respectable size, with a projected cost of approximately $500 million. In the grand scheme of space missions, this seemed like a perfectly reasonable ambition. It was a well-defined step forward, a logical progression from Hubble's triumphs. But as they delved deeper, as the engineers began to sketch and the physicists began to refine their desires, the universe, in its usual enigmatic fashion, began to reveal its true demands. It became clear, slowly but inexorably, that the universe's earliest stories weren't written in simple, accessible script. They were etched in the faintest, most stretched-out light imaginable, requiring an instrument of unprecedented sensitivity and scale. The initial $500 million budget began to seem like a small handful of pebbles attempting to fill an enormous chasm. Decision-makers, initially perhaps hesitant, came to a profound realization: achieving their aims, truly hearing those first whispers, would necessitate far, far more resources. It was akin to realizing that to build a bridge across a vast ocean, one cannot simply extend a sturdy wooden plank. An entirely new monumental feat of engineering would be required. So what exactly were these aims that demanded such an exponential leap in investment and effort? This brings us to the core of JWST's unique purpose, its profound connection to infrared light. Why infrared? Why this seemingly obscure sliver of the electromagnetic spectrum? The answer lies in some of the most fundamental, beautiful, and mind-bending facts about the universe itself. Our current understanding, a tapestry woven from decades of observation and theoretical brilliance, suggests that the universe as we know it has existed for roughly 13.8 billion years. How this all began is a question that has haunted humanity since the dawn of thought, a captivating enigma that has inspired countless myths, philosophies, and now scientific theories. The prevailing mainstream theory, the one that best fits the scattered clues we've meticulously gathered, revolves around the majestic concept of the Big Bang. Imagine, if you will, all the matter and energy of our vast universe compressed into a space so incredibly tiny, so infinitesimally small, that it was effectively zero. At that fleeting, impossible moment, atoms with their intricate dance of electrons and nuclei couldn't even exist. They would have been far too grand, too complex for such a hyperdense state. Then, in a flash, with a suddenness that defies our ordinary comprehension, everything began to expand outwards, not like an explosion in space, but like an expansion of space itself. This is a crucial distinction, often elusive yet central to our understanding. Think of it this way. Picture a balloon that is being steadily inflated. Now imagine tiny dots drawn onto the surface of this balloon. As the balloon expands, the dots move further and further away from each other. They aren't crawling across the rubber. The rubber itself, the very fabric of their space, is stretching, carrying them apart. This, in a simplified yet powerful analogy, is how our universe began its journey, expanding and cooling ever since that singular monumental event. As this cosmic balloon expanded, matter began to coalesce, first into the fundamental building blocks of atoms, then into swirling clouds of cosmic dust, which over vast stretches of time gravitationally collapsed to form the first magnificent stars, and then later the planets that now orbit them. But here lies the heart of the matter, the driving force behind the James Webb Space Telescope. Wouldn't it be immensely helpful, profoundly illuminating, To be able to turn back the hands of time to look directly into that initial fiery furnace of creation. To witness with our own cosmic eyes the formation of those very first galaxies, those primordial cities of stars. What insights, what profound truths might we glean about how it all happened? How the intricate cosmic tapestry began to weave itself. This is the fundamental yearning question that the JWST, now known as James Webb, was designed to answer. The James Webb Space Telescope stands as a sentinel at the precipice of this grand inquiry. It holds the potential to provide compelling evidence that reinforces our current understanding of the Big Bang, offering concrete observations that align with the theoretical framework we've painstakingly constructed. And this is the thrilling, humbling possibility that truly ignites the scientific spirit, it might just utterly transform our theories, challenging us to rethink the very genesis of our existence. It's a bold wager, a monumental investment in the pursuit of ultimate knowledge, driven by the profound understanding of how light travels. Light, that ephemeral shimmering messenger, is blindingly fast, yes. It races across the cosmos at an astonishing 299,792,458 meters per second exactly. But it is not instantaneous. There is always a tiny, almost imperceptible time delay between when a photon, a tiny particle of light, is emitted from its source, and when our eyes or our sensitive instruments finally perceive it. To bring this closer to home, consider our own sun. It sits approximately 148 million kilometers away from us, a comfortable, life-giving distance. This means that the golden sunlight warming your skin right now, the light illuminating the page before you, has been on a journey for approximately 500 seconds, or about 8 minutes and 20 seconds. So the sun you perceive shining brightly in the sky isn't the sun as it is right now in this very moment. It's the sun as it was 8 minutes and 20 seconds ago, a fleeting snapshot from its recent past. This subtle time delay, so negligible in our everyday lives, begins to unfurl into something truly profound when we consider the vast, mind-boggling distances of interstellar space. Take Proxima Centauri, our nearest stellar neighbor beyond the sun. It is so incredibly distant from Earth that the light from its gentle glow takes a staggering 4 years to finally reach our planet. When you gaze upon Proxima Centauri, you are not seeing it as it exists today, but as it appeared 4 years in the past. It's like receiving a letter from a friend who lives very far away. By the time you read their words, their circumstances may have already changed. This fundamental truth of light's finite speed has a powerful implication for objects that are further and further away from us. We are seeing them as they were further and further back in time. The cosmic distance suddenly transforms into a cosmic timeline. If, for instance, there was a celestial object positioned at an utterly immense distance from us so far that its light had been traveling for almost the entire age of the universe, we would effectively be seeing it as it was 13.8 billion years ago. We would be witnessing a direct echo of visual whisper from the very dawn of creation, near the origin of the universe itself. And here's where the universe, in its boundless generosity, seems to align with our deepest desires. As some wise voices speculate, we exist within an infinite universe. If this is truly the case, then such incredibly far-off objects, those ancient beacons of cosmic history, should indeed exist. They are out there waiting for us to find them, to gather their ancient light and decode their primeval tales. And with the James Webb Space Telescope, armed with its unparalleled sensitivity and its unique ability to see the universe in a different light, we hold the profound hope of finally being able to perceive them. It's like reaching out a hand across billions of years to touch the very first dewdrop of cosmic time. The concept of seeing these distant ancient objects is deeply intertwined with the peculiar nature of the light they emit, and this brings us back to the crucial question: why does the James Webb Space Telescope view in the infrared? This isn't just a technical detail. It's a fundamental key that unlocks the universe's most guarded secrets. One compelling reason, though, not the primary one for peering into the very early universe, is that infrared light possesses a remarkable ability to punch through the swirling veils of cosmic matter. Imagine vast, beautiful, yet incredibly dense clouds of gas and dust scattered throughout the galaxy, opaque barriers that block our view when we try to observe them with visible light. It's like trying to see through a thick fog-laden forest. Infrared light, with its longer wavelengths, can navigate these cosmic mists more effectively, allowing us to see past these otherwise impenetrable gas clouds and glimpse the hidden wonders, the newborn stars, the fledgling planetary systems that lie on the other side. It acts like a special kind of X-ray vision for the cosmos, revealing what is obscured to our ordinary sight. But the main reason, the profound and pivotal reason, the one that directly connects to our quest to observe those earliest galaxies, lies in a second, even more astonishing quirk of the universe: the undeniable fact that space itself is expanding. This isn't just galaxies moving through space. It's space stretching, carrying everything within it, further and further apart. The exact reasons for this cosmic expansion are still a deep, alluring mystery, a puzzle that continues to challenge the brightest minds. Current scientific theories lean towards the enigmatic concept of dark energy, a pervasive, unseen force that seems to be gently, yet persistently, pushing the fabric of the universe outwards, driving this grand, inexorable separation. Regardless of its ultimate cause, the observed reality is that everything in the universe is subtly, constantly moving away from everything else. It's like a quiet, ever-unfurling flower, its petals steadily growing apart. Now imagine a distant star, a beacon of light that is gracefully moving away from us due to this cosmic expansion. As the star recedes, the light waves it emits, those delicate ripples of energy, are stretched out. This phenomenon is elegantly known as the Doppler effect, a concept perhaps more familiar from the changing pitch of a siren as an ambulance speeds past. For light, however, it's not the pitch that changes, but the wavelength, and it's the wavelength of light that precisely defines the color we perceive. As these light waves are stretched, their wavelengths become longer, and this shift manifests as a gradual leaning, a subtle drift further and further towards the red end of the spectrum. We call this a redshift. The deeper we gaze into the universe, the further back in time we look, the more pronounced this redshift becomes. Scientists have observed a truly remarkable pattern. The further something is away from us, the faster it appears to be expanding away from us. This means that the light emanating from the very furthest galaxies, those ancient whispers from the dawn of time, has been stretched so incredibly far into the red part of the spectrum that it has actually gone beyond the visible red. It has transformed, becoming entirely invisible to our conventional eyes, shifting squarely into the infrared frequencies. Herein lies the elegant solution and the profound necessity of the James Webb Space Telescope. Hubble, for all its revolutionary capabilities, was not fully designed to detect these deeply redshifted infrared frequencies. It was a marvel for its time, but its ears weren't tuned to this particular crucial cosmic frequency. The James Webb Space Telescope, on the other hand, is specifically and exquisitely crafted for this very purpose. Its receptors are finely attuned to detect light with wavelengths ranging from 0.6 micrometers to a remarkably long 28.5 micrometers. Interestingly, this specialized tuning means that while James Webb is a master of the infrared, it actually cannot see all visible light frequencies. It can beautifully capture the vibrant reds and a substantial portion of the oranges in the visible spectrum. But beyond yellow, its vision blurs. It simply doesn't perceive those shorter wavelengths. Its entire focus, its magnificent purpose, lies squarely within the infrared frequencies. This unique specialization leads to an important distinction, one that NASA prefers to emphasize, to simply state that the James Webb Space Telescope is a replacement for Hubble is, in a factual sense, incorrect. At NASA, they prefer a more nuanced and perhaps more poetic description. James Webb supports and complements Hubble. They are not rivals vying for supremacy, but rather two magnificent partners, each with a distinct superpower. working in harmony to paint a more complete, vibrant portrait of the cosmos. Each telescope focuses on frequencies of light that the other does not see clearly, allowing for a panoramic and multifaceted view of the universe. Furthermore, with the potential for Hubble to continue its operations until 2040, it is quite likely that this grand old sentinel will actually outlast the projected maximum lifespan of the James Webb Space Telescope. This fact alone underscores the idea that Webb is not a successor, but a vital companion, a new lens that adds depth and dimension to our ongoing cosmic exploration. It would indeed make James Webb an odd replacement if its own journey were to conclude before its venerable predecessor. So while Hubble continues to unveil the universe in its familiar breathtaking visible colors, James Webb gazes into the hidden warmer tones, the deep ancient hues of infrared. Together they form a powerful duet, expanding our understanding of the universe in ways that neither could achieve alone. It's like having two artists each with a unique palette collaborating on a single infinitely complex masterpiece. One paints the vibrant immediate foreground, while the other meticulously renders the distant foundational layers, revealing the very bedrock of existence. This symbiotic relationship ensures that humanity's quest for knowledge is both broad and deep, encompassing the present wonder and the ancient past in a unified, harmonious vision. Now let us turn our attention to the silent, invisible engine that allows the James Webb Space Telescope to fulfill its extraordinary purpose, the very nature of light itself and its intimate dance with time. This is where the universe reveals one of its most profound secrets, not through a grand dramatic flourish, but through a constant, steady truth that underpins all we see and understand. Imagine for a moment that you are sitting by a vast, tranquil lake and a single perfect raindrop falls onto its surface. From that point, delicate concentric ripples begin to spread outwards, moving gracefully across the water. You instinctively know that these ripples take time to travel from where the drop first landed to the edge of the lake where you are watching. They are not instantaneous. Light, in a wonderfully similar fashion, behaves like these ripples. It bursts forth from its source, a star, a galaxy, even a fleeting atomic event. And then, like an invisible wave, it begins its journey across the immense cosmic ocean. While light is blindingly fast, a true cosmic sprinter racing at an astonishing 299,792,458 meters per second exactly, a speed that almost defies our comprehension. It is crucially not instantaneous. There is always a tiny, almost imperceptible time delay between the moment a photon, that minuscule particle of light, is born and emitted from its source, and the moment it finally reaches our eyes or the sensitive detectors of a telescope. It's a whisper traveling across an infinite silence, and even a whisper, however swift, must take its journey. To bring this cosmic truth closer to our everyday experience, let us consider our most familiar star, our very own sun. Our sun sits at a comfortable distance of approximately 148 million kilometers from us. This vast yet relatively close cosmic span means that the golden sunlight warming your skin. As you read this, the vibrant light illuminating the world around you embarked on its journey from the sun's fiery surface about 500 seconds ago. That's roughly 8 minutes and 20 seconds. So the sun you perceive shining brightly in the sky right now is not the sun as it exists in this precise moment. It is, in essence, a beautiful luminous snapshot of the sun as it was 8 minutes and 20 seconds ago. You are, in a very real sense, looking into its immediate past. This subtle, almost unnoticeable time delay in our daily lives begins to transform into something truly profound, something deeply meaningful when we stretch our gaze to the immense mind-boggling distances of interstellar and intergalactic space. Consider, for instance, Proxima Centauri, the nearest star to our own sun beyond our solar system. It is so incredibly distant from Earth, so many trillions of kilometers away, that the light from its gentle, persistent glow takes a full 4 years to finally complete its journey and reach our planet. When you gaze up at Proxima Centauri in the night sky, you are not seeing it as it exists right now in this very instant. You are seeing it as it was 4 years ago, a ghostly echo from its relatively recent cosmic history. This fundamental principle, this unchanging law of the universe, that light travels at a finite speed, has a breathtaking implication. It means that for objects that are further and further away from us, we are without exception seeing them as they were further and further back in time. The immense cosmic distance between us and a distant star or galaxy isn't just a measure of spatial separation. It's a living, breathing timeline. The deeper we peer into the vastness of space, the further back in cosmic history our sight extends. It's as if the universe is a grand ancient library, and each distant galaxy is a volume its pages open to a specific bygone era. Now imagine this concept pushed to its ultimate limit. If we could find an object positioned at an utterly immense distance from us, a celestial beacon so incredibly far away that the light it emitted at its birth had been traveling for almost the entire age of the universe, a journey of nearly 13.8 billion years, then we would be witnessing something truly extraordinary. We would be seeing that object as it was 13.8 billion years ago, a direct, unfiltered glimpse into the very earliest moments of creation, standing at the precipice of the universe's origin itself. It would be like seeing the first tiny buds of a cosmic garden just beginning to unfurl, and here, the universe in its boundless and often astonishing generosity seems to align perfectly with our deepest human desires to understand our beginnings. As many wise voices in the scientific community speculate, we exist within an infinite universe. If this grand hypothesis holds true, if the cosmos truly stretches without end, then such incredibly far-off objects, those primeval ancient beacons of cosmic history, should in fact exist. They are out there, silent and patient, waiting for us to find them, to patiently gather their ancient light, and to meticulously decode the primeval tales whispered across billions of years. And this is precisely where the magnificent purpose of the James Webb Space Telescope truly comes into its own. Armed with its unparalleled sensitivity, its colossal light-gathering mirror, and its unique ability to perceive the universe through the gentle ancient hues of infrared light, we hold the profound hope, the audacious ambition, of finally being able to perceive these almost impossibly distant, unimaginably old, cosmic entities. It's like reaching out a hand across the vast, silent ocean of time, attempting to touch the very first ripple of creation, to feel the initial stirrings of everything that has ever been. The quest to unlock these primordial secrets is what truly sets JWST apart. It isn't just about clearer pictures. It's about seeing the universe's baby pictures. Think of it as opening a family album stretching back countless generations, finding images so old they're barely discernible, faded by the relentless march of time. JWST is designed to restore those images, to bring their faint details into sharp focus, allowing us to understand the cosmic lineage that led to us. The implications of such observations are breathtaking. They could provide overwhelming, irrefutable evidence that firmly supports our current prevailing theory of the Big Bang, offering concrete observational anchors to the theoretical framework that describes the universe's explosive beginning. Imagine having a vivid photograph, finally, of those earliest moments, confirming what our equations have only been able to predict. Or, and this is the thrilling, humbling possibility that truly ignites the scientific spirit, the observations from James Webb might just utterly transform our current theories. What if the universe's infancy was subtly or even dramatically different from what our current models suggest? What if the first stars ignited in ways we hadn't anticipated? What if the earliest galaxies formed under conditions that challenge our most fundamental assumptions? This is the beauty of true scientific exploration. It's a journey into the unknown, a willingness to be surprised, to let the universe itself guide our understanding, even if it means discarding cherished ideas. It's the humility of acknowledging that our current knowledge is but a tiny lantern in an infinite darkness, and that every new observation is an opportunity for a brighter, more expansive illumination. This concept of seeing through time is not a whimsical notion, but a direct consequence of the physics of light. Every ray of starlight, every glimmer from a distant nebula is a traveler. It carries information about its source, not as it is now, but as it was when that light began its journey. The further away the source, the older the information. Thus, when James Webb captures light from the most distant reaches of the cosmos, it is essentially receiving messages from the deep past. These messages are like ancient scrolls weathered by eons, but filled with the stories of the universe's youth. The challenge, of course, is that these ancient scrolls are incredibly faint. Imagine trying to read a scroll from across a vast desert under the dimmest moonlight. The light from these primordial objects has spread out over billions of light years, becoming incredibly dilute, almost like a whisper that has traveled so far it's barely audible. This is why JWST's immense mirror, its vast light-gathering surface, is not just a technological marvel, but an absolute necessity. It is designed to capture every single precious photon, to collect every faint echo of that ancient light, like a cosmic butterfly net woven from the most sensitive fibers imaginable. Furthermore, the very nature of these ancient photons, these messengers from the dawn of time, undergoes a subtle but crucial transformation during their incredibly long journey. As the universe expands, as the fabric of space itself stretches like a colossal piece of elastic, these light waves are also stretched. This stretching lengthens their wavelength, pushing them from the realm of visible light, the colors our eyes can perceive, deeper and deeper into the infrared spectrum. This phenomenon, known as cosmological redshift, is the universe's way of encoding its age onto the very light it emits. So when James Webb looks for the oldest galaxies, it isn't searching for bright visible beacons. It's searching for the faintest, most deeply redshifted infrared glows. It's like trying to listen for a specific, very low-frequency hum in a vast, silent room. Most instruments would miss it entirely, but James Webb's detectors are exquisitely tuned to pick up precisely that ancient fundamental vibration. The journey of light from the universe's infancy to JWST's detectors is not just a physical one. It's a profound narrative. It speaks of the relentless expansion of space, the subtle dance of energy and matter, and the patient, unwavering march of cosmic time. Every photon collected by Webb tells a story not just of its origin, but of the entire vast expanse of cosmic history it traversed. It's a journey that began when the universe was in its earliest, most chaotic yet most fertile stages, a journey that ends billions of years later in the quiet, supercooled embrace of JWST's mirrors. And so, as we consider this dance between light and time, we begin to truly appreciate the incredible ambition and profound significance of the James Webb Space Telescope. It is not merely an instrument for observation. It is a time machine crafted from human ingenuity, powered by our insatiable desire to understand. It reaches back, not with a physical touch, but with the gentle, persistent embrace of light, to whisper to us the secrets of the cosmos's very first breath. As we drift toward slumber, let this thought settle gently in your mind. Somewhere out there, in the silent infinite darkness, light is still traveling, carrying ancient stories, waiting for a sensitive ear, a patient eye to finally receive its timeless message. Having journeyed through the intricate dance of light and time, let us now gently shift our focus to the very heart of the James Webb Space Telescope's unique power, its profound affinity for the infrared spectrum. This isn't merely a technical specification. It's a crucial key, a secret language that unlocks the universe's most profound and ancient narratives. Imagine the full spectrum of light as a magnificent invisible rainbow, stretching far beyond what our human eyes can perceive. Our eyes are beautifully adapted to see only a tiny sliver of this rainbow, the familiar colors of the visible spectrum, from vibrant reds to deep violets. Beyond the red, there's a vast, warm expanse called infrared. And beyond the violet, a cooler, energetic realm called ultraviolet, which Hubble could also glimpse. But to truly hear the universe's earliest whispers, we need to tune our ears, or rather our eyes, to those long, warm wavelengths of infrared. One compelling reason why infrared light is so invaluable, though not the primary driver for peering into the very early universe, is its remarkable ability to punch through the swirling veils of cosmic matter. Picture, if you will, the interstellar medium, the vast stretches of space between stars, not as an empty void, but as a diffuse, yet often incredibly dense tapestry woven from gas and dust. These cosmic clouds, while breathtakingly beautiful to our visible eyes, can be frustratingly opaque. They hide within them the very earliest stages of star formation, the nascent nurseries, where infant suns are being cradled, and the delicate construction sites where planetary systems are just beginning to take shape. Think of it like trying to see through a thick fog-laden forest on a misty morning. Your visible light vision is hampered. The fog scatters and absorbs the light, obscuring everything beyond a certain distance. But if you had a special kind of vision, perhaps one that could sense the warmth radiating from objects, you might be able to peer through the mist and discern the shapes of trees and creatures hidden within. Infrared light behaves in a similar fashion. Its longer wavelengths are less prone to being scattered or absorbed by the microscopic dust particles that make up these cosmic fogs. This allows the James Webb Space Telescope to act like a cosmic X-ray, letting us see past these otherwise impenetrable gas clouds and glimpse the hidden wonders, the newly forming stars, the fledgling planetary systems that lie on the other side. It's like pulling back a heavy velvet curtain to reveal a previously unseen stage of cosmic drama. But the main reason, the profound and pivotal reason, the one that directly connects to our quest to observe those earliest galaxies and truly understand the dawn of time, lies in a second, even more astonishing quirk of the universe, the undeniable fact that space itself is expanding. This is a concept that truly stretches the imagination. For it's not merely that galaxies are moving through a static space, like ships sailing on a calm sea. Instead, the very fabric of space, the sea itself, is stretching like a colossal piece of elastic, carrying everything within it further and further apart. The precise reasons for this cosmic expansion, particularly its accelerating nature, remain one of the universe's most alluring mysteries. It's a grand puzzle that continues to challenge the brightest minds, a whisper of a fundamental force we are only just beginning to comprehend. Current scientific theories gently point towards the enigmatic concept of dark energy, a pervasive, unseen force that seems to be subtly, yet persistently, pushing the fabric of the universe outwards, driving this grand, inexorable separation. Regardless of its ultimate hidden cause, the observed reality is undeniable. Everything in the universe is subtly, constantly moving away from everything else. It's like a quiet, ever-unfurling flower, its petals steadily growing apart from each other. Now imagine a distant star, a beacon of light that is gracefully receding from us due to this gentle, persistent, cosmic expansion. As the star moves away, the light waves it emits, those delicate ripples of energy are stretched out. This phenomenon is elegantly known as the Doppler effect, a principle we might intuitively grasp from the changing pitch of a siren as an ambulance speeds past, its sound waves being compressed as it approaches and stretched as it recedes. For light, however, it's not the pitch that changes, but the wavelength, and it's the wavelength of light that precisely defines the color we perceive. As these light waves are stretched by the expanding space, their wavelengths become longer. This subtle shift manifests as a gradual leaning, a gentle drift further and further towards the red end of the spectrum. This is what we beautifully term a redshift. The deeper we gaze into the universe, the further back in time we look, the more pronounced this redshift becomes. It's a direct consequence of the immense distances involved and the continuous expansion of space over those vast cosmic spans. Scientists have observed a truly remarkable pattern that reinforces this understanding. The further something is away from us, the faster it appears to be expanding away from us. This means that the light emanating from the very furthest galaxies, those ancient whispers from the dawn of time, has been stretched so incredibly far into the red part of the spectrum that it has actually gone beyond the visible red. It has transformed, becoming entirely invisible to our conventional eyes, shifting squarely, irrevocably into the infrared frequencies. It's as if the universe, in its grand unfolding narrative, is speaking to us in a voice that requires a special kind of listening. Herein lies the elegant solution and the profound necessity of the James Webb Space Telescope. Hubble, for all its revolutionary capabilities and its breathtaking contributions to our understanding of the cosmos, was simply not fully designed to detect these deeply redshifted infrared frequencies. It was a marvel for its time, a true pioneer, but its ears weren't finely tuned to pick up this particular crucial cosmic frequency. Imagine trying to hear a very low bass note with an instrument designed for high-pitched melodies. Hubble was magnificent at visible and ultraviolet melodies, but the bass notes of the early universe were simply beyond its range. The James Webb Space Telescope, on the other hand, is specifically and exquisitely crafted for this very purpose. Its sophisticated receptors are finely attuned to detect light with wavelengths ranging from 0.6 micrometers to a remarkably long 28.5 micrometers. This vast infrared reach allows it to capture the faint, stretched-out light from those first pioneering galaxies, giving us an unprecedented window into the universe's earliest moments. Interestingly, this specialized tuning to the infrared means that while James Webb is an unparalleled master of the warm long-wavelength light, it actually cannot see all visible light frequencies. It can beautifully capture the vibrant reds and a substantial portion of the oranges in the visible spectrum, painting these familiar colors with stunning clarity. However, beyond yellow, its vision blurs. It simply doesn't perceive those shorter, bluer wavelengths. Its entire focus, its magnificent purpose, lies squarely within the infrared frequencies, making it a specialist, a master of its chosen domain. This unique specialization leads to an important distinction, one that NASA and the broader scientific community prefer to emphasize, to simply state that the James Webb Space Telescope is a replacement for Hubble is, in a factual sense, incorrect. It's a common misconception, understandable given the immense public attention both telescopes command. However, at NASA, they prefer a more nuanced and perhaps more poetic description. James Webb supports and complements Hubble. They are not rivals vying for supremacy, like two athletes competing for the same prize. Instead, they are two magnificent partners, each with a distinct superpower, working in harmony to paint a more complete, vibrant portrait of the cosmos. Each telescope focuses on frequencies of light that the other does not see clearly, allowing for a panoramic and multifaceted view of the universe. Consider them as two master artists, collaborating on a single infinitely complex masterpiece. One artist, Hubble, paints with the vivid, immediate colors of the visible and ultraviolet spectrum, capturing the vibrant foreground and the details of galaxies closer to us, much like depicting a bustling city in broad daylight. The other artist, James Webb, meticulously renders the distant foundational layers, the ancient warmer hues of the infrared, revealing the very bedrock of existence, like painting the subtle glowing embers of a dying fire or the faint, distant lights of a primeval forest in the deep night. This symbiotic relationship ensures that humanity's quest for knowledge is both broad and deep, encompassing the present wonder and the ancient past in a unified, harmonious vision. Furthermore, a practical reality underscores this complementary relationship, with the potential for Hubble to continue its operations until 2040. It is quite likely that this grand old sentinel will actually outlast the projected maximum lifespan of the James Webb Space Telescope, which is estimated to be a maximum of 10 years. This fact alone underscores the idea that Webb is not a successor that renders the old obsolete, but a vital companion, a new lens that adds depth and dimension to our ongoing cosmic exploration. It would indeed make James Webb an odd replacement if its own remarkable journey were to conclude before its venerable predecessor. This collaborative spirit is a beautiful reflection of the scientific endeavor itself. No single instrument, no single mind can unlock all the universe's secrets. It is through the combined efforts of many, through diverse approaches and specialized tools, that we slowly, patiently peel back the layers of cosmic mystery. Hubble continues to capture breathtaking images of the universe's more recent history, revealing the intricate structures of nearby galaxies, the beautiful nebulae where stars are currently forming, and the dynamic processes happening right now in cosmic terms. Its data remains incredibly valuable for understanding the universe's evolution over billions of years. James Webb, on the other hand, is the deep diver, the archaeologist of light. It's built to penetrate the cosmic dust, to peer through the veils of gas, and to gather the stretched-out light from the most ancient distant objects. These are the objects that existed when the universe was in its infancy, barely a billion years old. Their light, by the time it reaches us, has been so profoundly redshifted that it is invisible to Hubble's primary detectors. Webb's mission is to capture these ghostly whispers, to decipher the earliest chapters of the cosmic story, to see the first stars ignite and the first galaxies coalesce from the primordial soup. Think of it as two different kinds of history books. Hubble gives us a detailed account of the last few chapters, rich with specific events and vibrant characters. James Webb, however, is tasked with uncovering the very first chapters, those faded, almost mythical accounts of how everything began. It might be challenging to read, requiring a specialized magnifying glass and a deep understanding of ancient scripts, but the information contained within is foundational. It tells us about the very origins of the language of the cosmos, the initial grammar and vocabulary that shaped everything that came after. The interplay between these two magnificent instruments is what truly excites the scientific community. When Hubble observes a distant galaxy, it might capture its visible light, revealing its present-day structure. But then, James Webb can turn its infrared eye to the same galaxy, or to the region behind it, to unveil hidden star formation within dusty lanes, or to find even more distant, redshifted galaxies that lie beyond Hubble's visible reach. They are not competing, but creating a richer, more comprehensive narrative together. This synergistic approach means that our understanding of the universe is not just expanded, but deepened. We can study the full life cycle of stars from their birth, hidden in dusty nebulae. Webb's strength, to their vibrant lives and eventual demise. Both Hubble and Webb contribute here. We can trace the evolution of galaxies from their nascent clumpy forms in the early universe. Webb, to the grand spirals and ellipticals we see today. Hubble, it's a holistic view integrating the past and the present, the hidden and the visible, into a single breathtaking cosmic tapestry. So as we settle into the quiet calm of the night, let us appreciate this beautiful partnership, this cosmic collaboration. While Hubble continues to grace us with its familiar stunning vistas, James Webb now stretches its sensitive sensors into the deepest, warmest parts of the spectrum, listening for the echoes of creation. Together, they are not just tools of science, but instruments of wonder, helping us to see and to understand the universe in its full magnificent glory. Having explored the profound reasons behind the James Webb Space Telescope's unique infrared vision, let us now embark on a quiet journey into the very heart of its being, its design, and groundbreaking technology. This is where the abstract ideas of physics meet the tangible art of engineering, where the dream of seeing the universe's earliest moments is meticulously forged into physical reality. Imagine for a moment that you are a meticulous watchmaker, tasked with creating the most complex, precise timepiece imaginable. Every gear, every spring, every tiny jewel must be crafted with absolute perfection, designed to mesh flawlessly, to whisper, rather than tick, to keep time not just for hours, but for eons. The James Webb Space Telescope, in its intricate design, is 1,000 times more complex, a cosmic timepiece meant to measure the very pulse of creation. At the core of Webb's observational power lies its magnificent primary mirror. Unlike Hubble's single vast disk, Webb's mirror is composed of 18 hexagonal segments each, a masterpiece of engineering in itself. These segments, when fully deployed and aligned in space, combine to form a colossal light-gathering surface, a single unified mirror that is 6.5 meters in diameter. To truly grasp the scale, consider that this surface area is a staggering 6 times larger than that of Hubble's mirror. It is without a doubt the biggest, most powerful mirror humanity has ever launched into the silent embrace of space. But why such an immense mirror? The answer circles back to our earlier contemplation of light and time. The light from those impossibly distant primordial galaxies, those faint echoes from the dawn of the universe, has traveled for billions of years. Over such colossal distances, this ancient light becomes incredibly dilute, almost like a whisper, carried across an endless desert, barely audible. Webb's colossal mirror acts as a vast sensitive collector, a cosmic butterfly net woven from the most precise materials designed to capture every single precious photon, every faint glimmer, every weak signal from these faint ancient sources. It is designed to gather more light, to listen more intently, allowing its instruments to pick up even the most elusive traces of radiation. The material used for these mirror segments is itself a story of innovation: beryllium. This choice was driven by a fundamental challenge: getting such a massive mirror into orbit. If engineers had used a material similar in weight to Hubble's mirror, Webb's colossal mirror would have been an astronomical 10 times heavier than it is now, far too massive for any existing launch vehicle to propel it to its final distant destination. Beryllium, however, is remarkably light, yet incredibly strong and stiff, capable of holding its precise shape, even under the extreme temperature fluctuations of space. This groundbreaking design means that each mirror segment, despite its impressive size, weighs a mere 20 kilograms, a triumph of lightweight high-performance engineering. One might then wonder, if beryllium is so wonderful, why isn't it always used for space telescopes? The answer lies in its peculiar nature. Beryllium is an exceptionally difficult metal to polish. To function correctly, Webb's mirrors had to be exquisitely smooth polished to a precision within nanometers, a smoothness that makes a human hair seem like a jagged mountain range in comparison. Achieving this level of optical perfection on beryllium added a significant layer of difficulty and painstaking precision to the building process, demanding new techniques and unparalleled craftsmanship. And then there's the gleaming, almost magical surface that covers these beryllium segments: gold. While beryllium provides the structural integrity, it's not ideal for reflecting infrared light. Gold, however, is a superb reflector of these warm, long wavelengths, making it the perfect choice for Webb's mission. You might look at the images of these golden mirrors and imagine vast quantities of precious metal. But here's another marvel of engineering. There is actually very little gold on them at all, less than 3 grams in total for the entire mirror assembly. How was such a microscopically thin, yet perfectly uniform layer of gold applied to such precisely polished surfaces? The technique they employed is nothing short of ingenious, a testament to human cleverness. Each mirror segment was meticulously placed inside a vacuum chamber. Then a minuscule amount of pure gold was vaporized into this chamber. The gold in its vapor form gently filled the chamber slowly and evenly, condensing onto all the surfaces within, including the highly polished beryllium mirror itself. This process, known as vapor deposition, ensured an extremely even atomic level finish, creating a perfectly reflective surface that could not have been achieved through any other method. It's like dusting the mirrors with the faintest, most delicate shimmer of cosmic stardust. Beyond the mirror's sheer size and exquisite construction lies another profound design challenge: how to fit a 6.5-meter wide mirror into the limited confines of a rocket. No existing launch craft could possibly accommodate a mirror of that rigid, monolithic size. This seemingly insurmountable obstacle led to one of Webb's most astonishing design features: its capacity to fold up and unfold. This isn't just a simple hinge. It's a complex, precisely choreographed mechanical ballet. The mirror segments, like sections of a delicate origami, are designed to fold back during launch, dramatically reducing the telescope's overall dimensions to fit within the 5-meter diameter fairing of the Ariane 5 rocket. This adds a massive amount of complexity to the design, as 18 hexagonal mirrors, once in space, must not only fold out, but also align themselves to nanometer precision to act as one seamless, perfect optical surface. As a result, not only do the mirrors fold out once launched, but each individual mirror segment can be controlled and adjusted individually to an incredibly fine degree using tiny hidden motors. It's like a colossal cosmic flower unfolding its petals, each movement calculated, each alignment perfect. The mirror, however, is only one part of Webb's intricate vision system. The telescope was also designed with the remarkable capability to view hundreds of objects simultaneously. Imagine trying to listen to hundreds of faint, distant conversations at once and needing to isolate each voice and understand what it's saying. This almost impossible feat is achieved through some truly groundbreaking innovations invented specifically for James Webb technologies, so advanced that they promise to benefit many other sectors, from biotechnology and medicine to cutting-edge communication systems. Specifically, this capability relies on an astonishing array of microshutters. Think of these as tiny individual windows, each only the width of a few human hairs, that can be opened or closed independently. By precisely controlling which tiny windows are open, the telescope can isolate the light from hundreds of distant individual objects, be it stars or galaxies, while blocking out the overwhelming glare from brighter nearby sources. This allows Webb to simultaneously measure the intensity and spectra of light from these many faint distant objects at the same time. While spectroscopic technology, the science of breaking light down into its constituent colors to reveal its chemical fingerprints, isn't new, the ability to perform this analysis on up to 100 separate objects simultaneously represents a monumental leap forward. Each tiny band of light gathered is an individual spectroscopic reading, a unique story being told by photons from a different corner of the universe. The sheer precision and miniaturization of these microshutters are truly mind-boggling. Beyond these ingenious shutters, the very infrared camera sensors themselves are bespoke devices that had to be designed specifically for this telescope. These are state-of-the-art and representing the biggest and most sensitive infrared detectors ever made. Webb carries 3 different types of detectors, each optimized for different wavelengths within the infrared spectrum. These detectors are incredibly advanced, going beyond simply taking one sample per pixel. Instead, they capture several samples per pixel, a sophisticated technique that allows them to dramatically reduce noise in the data, the random fluctuations that can obscure faint signals. Furthermore, this multi-sampling allows them to effectively sense if a cosmic ray, a high-energy particle from space, happens to strike a pixel. If such an event occurs, the system can identify it and effectively cancel it out, preventing the spurious signal from contaminating the precious data. It's like having a cosmic filter, ensuring only the truest whispers of light are heard. Another paramount design issue that engineers had to address with immense care was excess heat. As we explored earlier, infrared telescopes are exquisitely sensitive to heat. Even the minuscule amount of heat generated by the telescope's own internal parts could potentially blind its incredibly sensitive sensors, overwhelming the faint infrared signals from distant cosmic sources. Imagine trying to observe the delicate shimmer of a distant candlelight while standing next to a roaring bonfire. The heat from the bonfire would completely obscure the candlelight. To combat this internal heat, A sophisticated radiator system is designed into one side of the telescope. This passive cooling system enables the telescope to radiate away any heat it generates itself into the cold vacuum of space. The goal is to keep the majority of the instruments at a frigid 228 or 53 Kelvin. This is a temperature far colder than the coldest recorded temperature on Earth, a stark, profound chill. However, one of the instruments aboard the James Webb Space Telescope, the mid-infrared instrument MIRI, requires even more extreme temperatures. MIRI is designed to observe longer, warmer infrared wavelengths, and to do so without interference, it must operate at an astonishingly cold 7 Kelvin or 266 degrees C. This is just a few degrees above absolute zero, the theoretical point where all atomic motion ceases. To achieve and maintain this incredible chill, MIRI needs its own dedicated cryocooler. Think of this as a super advanced miniature refrigerator in space. It's essentially a closed-loop system where cold helium gas flows through a pipe, constantly circulating past the instrument, drawing away any minuscule heat, and returning to a pump at the bottom of the spacecraft to be recooled. The very idea of a pump operating in such a sensitive environment presents another engineering conundrum. Pumps by their nature create vibrations, and even the slightest vibration could introduce blurring or instability to Webb's incredibly precise observations. Thus, a super low vibration pump had to be developed, a marvel of quiet mechanics designed to operate with such minimal disturbance that it would not interfere with the delicate business of gathering faint light from the edge of the universe. It's like building a silent heart for the coldest part of the telescope, ensuring its quiet, steady function. These intricate design solutions, from the golden folding mirrors to the whispering cryocoolers, are not just feats of engineering. They are poetic expressions of humanity's boundless ambition, our persistent curiosity, and our unwavering commitment to reaching beyond the familiar, to touching the very edge of the knowable, and to listening to the oldest, faintest whispers that the universe has to offer. They are the tangible realization of a dream, to see the invisible, to hear the silent, and to understand the profound depths of cosmic time. Having marveled at the intricate details of Webb's golden folding mirror and its advanced supercooled instruments, let us now turn our gaze outward beyond the Earth to understand the strategic genius behind its placement in the vast expanse of space. This brings us to a profound concept, the Lagrange points, and specifically Webb's chosen sanctuary, the L2 Lagrange point. Imagine for a moment the intricate cosmic dance of planets and stars, each performing its gravitational ballet. In such a system, there exist special locations, points of gravitational equilibrium, where the gravitational forces of two large celestial bodies, in our case, the Sun and the Earth, balance each other out. These are known as Lagrange points, named after the brilliant mathematician Joseph Louis Lagrange. There are 5 such points in any two-body system, like a tiny handful of perfect invisible pockets in the grand cosmic fabric. Webb will gracefully orbit around one of these, the L2 Lagrange point. This position in space, while technically not a true orbit around the Earth, in the way the Moon orbits us, exists approximately 1.5 million kilometers, about 930,000 miles from the Earth, situated directly opposite the Sun. To give you a sense of scale, the Moon, our familiar celestial companion, is much closer, orbiting at an average distance of about 384,000 kilometers, so Webb will be significantly further out, a solitary sentinel, almost 4 times more distant than the Moon. Why this particular far-flung cosmic perch? The reasons are multifaceted and deeply connected to Webb's core mission of observing the universe in infrared light. Firstly, being so far out in space, Webb does not have to contend with the Earth's turbulent, light-distorting atmosphere. Imagine trying to observe the delicate shimmer of a distant light through miles of rippling heat-hazy air. That's what ground-based telescopes often battle. Even the mighty Hubble, though in orbit, is still relatively close to Earth, and while it avoids much of the atmospheric distortion, it's not in the complete pristine vacuum that Webb enjoys. The vacuum of deep space provides an incomparably clear view, an utterly unblemished window, allowing James Webb to find those tiny diffuse infrared waves much more easily without any atmospheric interference, scattering, or absorbing them. It's like having perfect unclouded vision for the most subtle cosmic details. Secondly, the L2 point offers unparalleled thermal stability, which is absolutely critical for an infrared telescope. Remember how exquisitely sensitive Webb's instruments are to heat. Any warmth, even from the telescope itself, could overwhelm the faint infrared signals it seeks to capture. At L2, Webb can always keep the Earth, the Moon, and the Sun positioned behind its massive sunshield, blocking out their intense heat and light. This means the telescope's delicate scientific instruments can consistently remain in a state of extreme cold, shielded from any radiation bouncing off the Earth or the Moon. It's like finding the perfect perpetual shadow in the vast, brightly lit cosmic expanse. Yet despite its distant location, L2 is still close enough for practical communication. Webb needs to send vast amounts of precious scientific data back to Earth, telling us what wonders it sees and what ancient whispers it hears. This balance of being far enough to escape thermal and atmospheric interference, yet close enough for robust communication, makes L2 an almost ideal cosmic staging ground for a mission of this nature. Naturally, at such a distant position, it will be incredibly difficult for us to visit the James Webb Space Telescope. Unlike Hubble, which famously received several servicing missions from space shuttles to upgrade its instruments and repair its components, Webb is essentially beyond our reach. So while James Webb was designed with a docking ring for hypothetical future visits, it is currently planned that there will be no missions to service or replace its parts once it's up there. This one-shot nature means that every single step of its deployment and operation must be meticulously planned and executed with absolute perfection. It's a grand cosmic experiment where failure is simply not an option. This self-sufficiency brings us to a crucial yet often bittersweet detail about Webb's lifespan. Although it needs minimal effort to maintain its precise position around the L2 point, minimal is not zero. Webb requires a small amount of fuel to periodically fire its thrusters, making tiny adjustments to stay in its precise halo orbit around L2, correcting for the subtle gravitational tugs from the Sun and Earth. James Webb has enough fuel to maintain this delicate dance for at least 5 years and at most 10 years. After that, its fuel will eventually deplete, it will decay from its finely tuned orbit, and it will no longer function as intended. It has woven into its very existence a guaranteed expiration date. Why build something so magnificent, so complex, so costly, only for it to last a maximum of a decade? This question echoes our earlier ponderings, and the answer remains profound. The unique, unparalleled access it provides to the early universe, a window that no other instrument can offer. Its limited lifespan underscores the urgency and value of every second it operates, knowing that each photon collected is a precious non-renewable resource from the dawn of time. One final beautiful benefit of this distant, serene L2 position, intimately linked with its thermal stability, is the temperature itself. As we know, heat travels in infrared waves. The heat generated by the telescope's own electronic parts and instruments, if left unchecked, could potentially blind its own incredibly sensitive sensors. It would be like trying to listen for a faint whisper in a room filled with roaring furnaces. However, thanks to its strategic position in space, perpetually shielded from the Sun, Earth, and Moon, James Webb will be able to cool itself passively to astonishingly low temperatures, reaching a frigid 223 degrees or 50 Kelvin for most of its instruments. This deep chill is also profoundly aided by its most distinctive visual feature, its enormous solar shield. You have no doubt noticed the large, shimmering silver canvas at the bottom of the satellite in images. This isn't just a simple sheet. It's a meticulously engineered 5-layered shield, each layer incredibly thinner than the width of a human hair. This colossal shield, which unfurls to the size of a tennis court, roughly 20 meters by 14 meters, is precisely designed to point constantly in the direction of the Sun, Earth, and Moon, effectively blocking the heat radiating from them. The effect is dramatic. While the sun-facing side of the shield can reach nearly 100 degrees C's boiling point, the instruments on the shielded side remain at that astonishingly cool 223 degrees Celsius. This extreme temperature differential is what allows Webb's infrared detectors to function with unparalleled sensitivity, picking up the faintest, coldest infrared signals from the farthest reaches of the cosmos without being overwhelmed by its own internal warmth. With that last fact, you may have begun to truly realize the immense scale of this satellite. It is vast. Roughly 20 meters by 14 meters, and weighing almost 6,200 kilograms, about 13,600 pounds, it is a colossal instrument. This naturally raises a fundamental engineering question, one that has occupied brilliant minds for decades. How on Earth, or rather from Earth, are they going to get this monstrous yet exquisitely delicate telescope into its distant orbit? This seemingly impossible feat is explained by one of the most frankly astounding engineering aspects of this telescope: its extraordinary capacity to fold up and unfold. This is where the quiet art of origami meets the monumental ambition of space exploration. The Ariane 5 rocket chosen as Webb's launch vehicle, a significant contribution from the European Space Agency to this international endeavor, has a fairing or cargo bay with a diameter of only 5 meters. Clearly, a 6.5 meter wide mirror and a tennis court-sized sunshield would not fit in their deployed states. As such, James Webb has been designed as a complex, meticulously choreographed marvel of deployable structures. Its primary mirror can fold inward, its secondary mirror arm can fold down, and most dramatically, its enormous multi-layered sunshield can be precisely folded like a giant intricate blanket, reducing its total dimensions to an incredibly compact form while it is nestled within the rocket. It's like packing a grand complex ship into a tiny bottle, every piece intricately designed to fit perfectly. Once it has been launched, and while it is traversing the cold, silent void of space on its journey to the L2 Lagrange point, the James Webb Space Telescope will begin its gradual, delicate, and utterly critical unfolding process. This is not a rapid, sudden unfurling, but a slow, deliberate ballet of precision engineering. Arms will gracefully unfold, hinges will silently articulate, the multi-layered shields will meticulously unspool and tension themselves into their vast, kite-like configuration. Finally, the hexagonal segments of the primary mirror will rotate into their precise positions, then align themselves with the aid of tiny, perfectly flush motors, each adjusted to nanometer precision. Every single movement, every subtle click into place is pre-programmed and utterly critical. All these intricate, delicate movements are orchestrated to allow it to go about its incredibly sensitive business of gathering radiation from the dimmest, most ancient lights in the sky. Mastering this process, the art of getting such an unbelievably sensitive and complex device into orbit without something breaking or malfunctioning during its elaborate deployment, is precisely the reason James Webb has taken so long to build. Decades of work, billions of dollars, countless hours of meticulous testing and retesting have been poured into ensuring this unfolding ballet is nothing short of perfection. Remember, the stakes are impossibly high once launched. There is absolutely no chance of going up there and fixing it if something breaks during deployment. Unlike Hubble, which could be serviced by astronauts, Webb's distant L2 perch makes such a mission impossible with current technology. If even one critical component were to fail during its complex unfurling sequence, if a hinge jammed, a cable snagged, or a motor failed, it could well spell the premature end of the entire mission, rendering over 2 decades of dedicated work and $9.7 billion effectively wasted. This is why the testing process has been so exhaustive, so painstaking, and so time-consuming, pushing the boundaries of what is possible in space engineering. The history of Webb's development is punctuated by these moments of intense scrutiny and redesign. In 2005, just a few years before its initial intended launch date, the entire project underwent a fundamental redesign. Every system, every component, every process was checked and double-checked by independent review boards anticipating every conceivable point of failure. Later in 2018, the project faced a further significant delay when a critical test of deploying the massive solar shield ended up with a section of it ripping. This forced engineers to pause, meticulously review what went wrong, and implement fixes. The review found an additional 344 potential single-point failures, any one of which, if it broke, would mean the entire thing would no longer work. This level of fragility and complexity is staggering, a constant reminder of the fine line between triumph and failure in such an ambitious endeavor. Even beyond the technical challenges, the project faced existential threats. When costs started rising dramatically in 2011, the American Congress, in an effort to reduce NASA's budget, moved to effectively cancel James Webb entirely. It was a moment of profound crisis for the scientific community, a dark cloud hanging over 2 decades of tireless effort. However, the public backlash, a powerful wave of support for the project from scientists, enthusiasts, and ordinary citizens around the world, ultimately led them to reverse their decision. This outpouring of collective belief in the value of scientific discovery saved the mission, a testament to the idea that the pursuit of knowledge resonates deeply within the human spirit. James Webb, therefore, is not just a triumph of engineering. It is a triumph of perseverance, of international collaboration, and of collective human will. Built by NASA in cooperation with the European Space Agency and the Canadian Space Agency, it has been delayed over 13 times. Its project costs have increased from that initial modest $500 million to a staggering $9.7 billion. But finally, after decades of waiting, of planning, of building, and of testing, it is here. Its mission to peer into the heart of space and uncover the mysteries of the formation of the first galaxies, stars, and planets has finally begun. You can be absolutely certain that when it launched from the European spaceport in French Guiana, there were countless people, scientists, engineers, space enthusiasts, and dreamers, waiting for news of a successful launch with bated breath, their hopes suspended on every delicate maneuver. And you can also bet that now it's in the sky, its instruments cooling and aligning. Scientists from every corner of the globe will be fighting tooth and nail for the precious limited time to get a chance to look through it, to be among the first to discover what wonders it sees and what ancient secrets it unveils. So to all the teams involved with this incredible project, good luck for the continued deployment and the mission ahead. If it works, and by all indications it is working magnificently, this instrument will be the biggest thing for space science for potentially decades to come. It is more powerful than any other space telescope, including Hubble. So big it had to be folded up like origami to fit onto the rocket that carried it into space. So precise and sensitive, it has to be kept at temperatures not much warmer than absolute zero to prevent its own internal heat radiation from getting in the way of its sensors. So expensive, it cost $10 billion to make, and so complicated it took decades to complete, with hundreds of potential failure points standing between it and proper functionality. But now it is here, a testament to what humanity can achieve when it dares to dream beyond the stars. As we continue our quiet journey through the universe, let us now gently unpack the technological wonders that reside at the very core of the James Webb Space Telescope. Its extraordinary scientific instruments. If the mirror is Webb's keen eye, then these instruments are its intricate, sensitive brain, meticulously designed to decipher the faintest whispers and the most ancient stories carried on the cosmic winds. Imagine for a moment an orchestra. The primary mirror is like the vast, beautifully curved concert hall, designed to capture every note, every subtle resonance. But without the musicians and their finely tuned instruments, that hall, however grand, would remain silent. Webb's scientific instruments are those musicians, each one a master of a particular cosmic symphony, capable of extracting profound meaning from the seemingly chaotic influx of light. One of the most astonishing capabilities of the James Webb Space Telescope lies in its ability to view hundreds of objects simultaneously. This is not a simple feat. Imagine trying to listen to hundreds of faint, distant conversations all at once in a crowded room and needing to isolate each individual voice, understand its language, and grasp the meaning of its unique story. This seemingly impossible task is made real through some truly groundbreaking innovations, technologies so exquisitely advanced that they were invented specifically for James Webb. The beauty of these inventions is that they promise to ripple outwards, benefiting many other sectors far beyond astronomy, from the delicate precision required in biotechnology and medicine to the complex data handling in cutting-edge communication systems. The key to this simultaneous observation is an astonishing array of tiny, incredibly precise devices known as microshutters. Think of these not as windows, but as minuscule, independently controllable apertures, each no wider than a few human hairs. There are literally hundreds of thousands of these microscopic shutters arranged in a grid. By precisely controlling which tiny shutters are opened and which are closed, the telescope can meticulously isolate the light emanating from hundreds of distinct individual objects, be they distant stars forming planetary systems or entire primeval galaxies, while simultaneously blocking out the overwhelming glare from much brighter nearby sources. It's like having an invisible microscopic hand that can selectively pick out only the exact light rays you wish to study, discarding all the overwhelming noise. This ingenious system allows Webb to perform spectroscopy on multiple targets at once. Spectroscopy is the science of breaking light down into its constituent colors, much like a prism separates white light into a rainbow. Each element and molecule in the universe absorbs or emits light at very specific unique wavelengths, leaving behind a kind of chemical fingerprint in the light's spectrum. By analyzing these fingerprints, scientists can decipher the chemical composition, temperature, density, and even the motion of distant celestial objects. While the fundamental concept of spectroscopy isn't new, the ability to perform this incredibly detailed analysis on up to 100 separate objects at the exact same time represents a monumental leap forward in astronomical observation. Imagine the efficiency. Instead of painstakingly analyzing one star at a time, Webb can gather a symphony of information from 100 different cosmic sources in a single observation. Each tiny band of light, gathered by a microshutter, is an individual spectroscopic reading a unique story being told by photons, allowing us to uncover the hidden chemical makeup of the universe across vast distances. The sheer precision and miniaturization required for these hair-width microshutters are truly mind-boggling, a testament to human ingenuity pushed to its limits. Beyond these ingenious shutters, the very infrared camera sensors themselves are bespoke devices, entirely new creations that had to be designed specifically for this telescope. These are not off-the-shelf components. They are state-of-the-art marvels representing the biggest and most sensitive infrared detectors ever made. Webb carries 3 different types of detectors, each meticulously optimized for different wavelengths within the expansive infrared spectrum. This allows Webb to cover a vast range of infrared light, from the very shortest near-infrared wavelengths that border on visible light to the longest far-infrared wavelengths that reveal the coldest, dustiest regions of the cosmos. What makes these detectors so advanced is their unique operational philosophy. They don't just take one fleeting sample per pixel, but several. This sophisticated technique allows them to dramatically reduce what scientists call noise in the data, the random fluctuations and interference that can obscure the faint, precious signals from distant cosmic sources. Think of it like taking multiple photographs of a very dim object. By combining them, you can filter out the random imperfections in each individual shot, revealing a clearer, more resolute image. Furthermore, this multi-sampling capability allows these detectors to effectively sense if a cosmic ray, a high-energy particle zipping through space, happens to strike a pixel. Cosmic rays can create false signals like sudden unwanted flashes in a photograph. If such an event occurs, the system can precisely identify it and effectively cancel it out, preventing the spurious signal from contaminating the precious data. It's like having an invisible, vigilant cosmic filter, ensuring that only the truest whispers of light are heard and recorded free from cosmic interference. The profound sensitivity of these instruments brings us back to a critical engineering challenge: excess heat. As we have discussed, infrared telescopes are exquisitely sensitive to warmth. Any heat, even the minuscule amount generated by the telescope's own electronic parts, could overwhelm its incredibly sensitive sensors, making it impossible to pick up the faint infrared signals from distant celestial objects. Imagine trying to listen for a faint, distant whisper in a room filled with roaring furnaces. The heat and noise from the furnaces would completely obscure the whisper. To combat this relentless internal heat, a sophisticated radiator system is intricately designed into one side of the telescope. This is not an active cooling system with moving parts, but a passive one relying on the principles of thermal radiation. It enables the telescope to radiate away any heat it generates itself into the profound cold of space. The primary goal is to maintain the majority of Webb's sensitive instruments at an astonishingly frigid temperature of -120 degrees or 53 Kelvin. To put that into perspective, this temperature is far colder than the coldest recorded temperature on Earth's surface, a stark, deep chill that allows the faint infrared light to be detected without interference. However, one particular instrument aboard the James Webb Space Telescope, the mid-infrared instrument MIRI, requires even more extreme, almost impossibly cold temperatures. MIRI is specifically designed to observe longer, warmer infrared wavelengths, which are particularly susceptible to even the slightest thermal interference. To do its job without interference, MIRI must operate at an astonishingly cold 7 Kelvin or 266 degrees Celsius. This is just a mere few degrees above absolute zero, the theoretical point where all atomic motion completely ceases. To achieve and maintain this incredible, supercooled state, MIRI needs its own dedicated cryocooler. Think of this cryocooler as a super advanced miniature refrigerator operating in the vacuum of space. It's essentially a closed-loop system where cold helium gas chilled to extreme temperatures flows continuously through a pipe circulating tirelessly past the MIRI instrument. As it circulates, this cold helium gently draws away any minuscule heat generated by MIRI, then returns to a pump at the bottom of the spacecraft to be recooled and sent back through the loop. This constant silent circulation ensures MIRI remains at its operational temperature. The very idea of a pump operating in such a sensitive, vibration-intolerant environment presented yet another profound engineering conundrum. Pumps, by their nature, involve moving parts that create vibrations, and even the slightest vibration could introduce blurring instability or noise to Webb's incredibly precise observations. Thus, a super low vibration pump had to be developed specifically for MIRI's cryocooler. This pump is a marvel of quiet mechanics, designed to operate with such minimal disturbance, such an imperceptible hum, that it would not interfere with the incredibly delicate business of gathering faint light from the edge of the universe. It's like building a silent heart for the coldest part of the telescope, ensuring its quiet, steady function allows the most profound observations to be made without disturbance. And finally, capping off this symphony of thermal management is the most distinctive visual feature of the entire James Webb Space Telescope, its enormous shimmering solar shield membrane. You have no doubt noticed the large reflective silver canvas at the bottom of the satellite in images and artistic renderings. This isn't just a simple sheet. It's a meticulously engineered 5-layered shield, each layer incredibly thin, actually thinner than the width of a human hair. This colossal shield, when fully unfurled, expands to the impressive size of a tennis court, roughly 20 meters about 69 feet by 14 meters about 46 feet. Its ingenious design allows it to be precisely pointed constantly in the direction of the sun, earth, and moon, effectively blocking the intense heat and light radiating from them. The thermal performance of this shield is truly astonishing. While the sun-facing side of the shield can reach nearly 100 degrees Celsius, the boiling point of water, the delicate instruments on the permanently shielded cold side remain at that astonishingly frigid 223 degrees Celsius or 50 Kelvin. This extreme temperature differential maintained across the thin layers of the shield is what allows Webb's infrared detectors to function with unparalleled sensitivity, picking up the faintest, coldest infrared signals from the farthest reaches of the cosmos without being overwhelmed by any ambient warmth or its own internal heat. It's a passive thermal masterpiece, a cosmic umbrella creating a perpetual shadow in the searing light of space. Of course, due to the inherent launch limitations, the simple fact that a tennis court-sized object cannot fit into a rocket fairing. This immense membrane, like the mirror, must start out folded away. And when it reaches space, it will begin the intricate, delicate ballet of its unfolding. This isn't a rapid dramatic snap open. Instead, it's a slow, meticulous process that unfolds over the course of several days with hundreds of tiny motors, pulleys, and cables working in concert, gently pulling the membrane outward until it is fully stretched and tensioned. Every single step of this deployment is critical and fraught with potential challenges. In fact, this membrane deployment process was one of the reasons for a significant delay to the telescope's launch schedule. During a critical test of this deployment process, back in 2018, a section of one of the delicate membranes unfortunately ripped. This forced the engineers to pause the entire project, meticulously investigate what went wrong, and implement precise fixes and reinforcements to ensure that such a catastrophic failure would not occur during the actual one-time launch and deployment in space. This incident, while a setback, underscores the immense complexity and the painstaking attention to detail required for every component of Webb. Because this is the overarching critical truth about the James Webb Space Telescope. If something goes wrong, there is no way to fix it once it's in space. Unlike the Hubble Space Telescope, which orbited close enough to Earth for astronauts aboard space shuttles to visit and perform intricate repairs and upgrades, Webb's distant L2 perch makes such a human servicing mission impossible with current technology. This means that every single aspect of its design, every component, every wire, every hinge, every motor, and every step of its deployment sequence must be absolutely perfect. Engineers and scientists have to ensure that they do everything within their power to get it right the very first time, because there are no second chances in the cold, unforgiving vacuum of deep space. With such a profoundly complicated design involving hundreds of thousands of individual parts, there is so much that could go wrong, so many potential points of failure. Just look at the launch and deployment process from a distance for it to get to its final orbital location. That serene L2 Lagrange point behind the Earth and beyond the orbit of the Moon is a journey of incredible precision and risk. It's crazy to contemplate. Nothing of this scale and complexity with so many critical one-time deployment maneuvers has ever been attempted before in human spaceflight, and it is unlikely anything will match it for a while to come. These intricate design solutions, from the golden folding mirrors and the hair-width micro-shutters to the whispering cryo-coolers and the tennis court-sized sunshield, are not merely feats of engineering. They are poetic expressions of humanity's boundless ambition, our persistent curiosity, and our unwavering commitment to reaching beyond the familiar to touching the very edge of the knowable. They are the tangible realization of a dream, to see the invisible, to hear the silent, and to understand the profound depths of cosmic time, a dream nurtured and brought to fruition through decades of tireless dedication. We have journeyed through the intricate design and the awe-inspiring technology that defines the James Webb Space Telescope, a machine of unprecedented ambition. But behind every gleaming mirror and every precisely aligned instrument lies a human story, a saga of relentless perseverance, moments of profound doubt, and ultimate triumph against staggering odds. Let us now reflect upon the challenges and significant events that marked the arduous path of Webb's development, a journey that truly tested the limits of human ingenuity and patience. Imagine if you were embarking on a colossal endeavor, something akin to building a magnificent sprawling city in the clouds. You begin with a dream, a vision of what it could be. In 1996, when the concept of the next-generation space telescope first began to stir, it was a modest dream perhaps, like planning a charming small town. The initial estimate for its construction was a relatively contained $500 million, with an optimistic launch date set for 2007. These numbers, in retrospect, seem almost quaint, a whisper from a bygone era of perceived simplicity. But as the detailed planning commenced, as the brilliant minds began to grapple with the sheer scale of the scientific ambition, peering into the very first moments of the universe, the true complexity of the task began to unveil itself. The requirements for the mirror's size, the need for extreme cold, the necessity of complex unfolding mechanisms, and the demand for unparalleled sensitivity all started to push against the boundaries of existing technology. It was like realizing that your charming small town needed to be a futuristic metropolis hovering above the ground, powered by technologies not yet invented. This escalating complexity led to a relentless march of delays and cost increases. The projected launch date, once a firm beacon, began to recede into the future, shifting from 2007 to 2011, then to 2014, and further still, ultimately being delayed over 13 times before its eventual launch in late 2021. And with each delay, each unforeseen technical hurdle, each redesign, the budget swelled. From that initial $500 million, the cost ballooned to a staggering $9.7 billion. This was no longer a small town in the clouds. It was a cosmic megastructure, a testament to an ambition that seemed to know no bounds. This protracted development and spiraling cost created immense pressure, leading to periods of profound uncertainty. Imagine devoting 2 decades of your life, your intellect, your passion to a single monumental project, only to see it constantly teetering on the brink of cancellation. The very nature of Webb's design introduced unprecedented deployment risks. As we explored earlier, this telescope is a master of cosmic origami, designed to fold itself into a compact package for launch and then meticulously unfurl in the unforgiving vacuum of space. The primary mirror, the secondary mirror, the sun shield. Each component has a complex single-shot deployment sequence. There are hundreds of motors, thousands of hinges, and miles of cables involved. And here lies the critical, terrifying truth. Once launched, there is absolutely no chance of going up there and fixing it if something breaks during deployment. Unlike the beloved Hubble, which orbited relatively close to Earth and famously received several servicing missions from space shuttle astronauts, Webb's distant perch at the L2 Lagrange point makes human intervention impossible with current technology. This one-shot nature instilled a profound sense of gravity into every single test, every single component check. It meant that every engineering team had to aim for absolute perfection, because the consequence of even a minor flaw could be the catastrophic failure of the entire mission, rendering decades of work and billions of dollars effectively wasted. It was like preparing for a high-wire walk across a canyon, knowing that there is no net below and every single step must be flawless. The history of Webb's development is punctuated by these moments of intense scrutiny and redesign, born out of this inherent risk. In 2005, just a few years before its initial intended launch date, the entire project underwent a fundamental redesign. This wasn't a minor tweak. It was a comprehensive re-evaluation of every system, every component, and every process. Independent review boards meticulously checked and double-checked everything, anticipating every conceivable point of failure, scrutinizing every design choice to mitigate risk. It was an acknowledgement that the initial plans, while ambitious, had underestimated the true complexity required for such a pioneering mission. Later in 2018, the project faced a further significant delay caused by a critical setback during ground testing. A crucial test of deploying the massive solar shield, that tennis court-sized, multi-layered membrane, ended with a section of it ripping. This was a devastating moment, a stark reminder of the delicate nature of the technology. The incident forced engineers to halt the entire project, meticulously investigate what went wrong, identify the root cause, and implement precise fixes and reinforcements to ensure that such a catastrophic failure would not recur during the actual irreplaceable launch and deployment in space. This painstaking review process uncovered an additional 304 potential single-point failures, meaning any one of these individual components breaking would lead to the entire mission no longer working as intended. The sheer number of these potential vulnerabilities speaks volumes about the incredible complexity and inherent fragility of the telescope, underscoring the razor-thin margin between success and failure. Beyond the technical hurdles, the James Webb Space Telescope faced existential threats that almost brought its journey to a premature end. As costs continued to escalate dramatically, particularly in 2011, the American Congress, in an effort to curb escalating budgets and exercise fiscal responsibility, moved to effectively cancel James Webb entirely. This was a moment of profound crisis for the scientific community worldwide. Decades of tireless effort, billions of dollars invested, and countless dreams hung in the balance, threatened by a single stroke of a pen. However, in a truly remarkable display of collective human will and passion, the project was saved by an unprecedented wave of public backlash and support. Scientists, space enthusiasts, educators, and ordinary citizens from around the world rallied. They wrote letters, signed petitions, and voiced their fervent support for the mission, articulating its profound scientific value and its potential to inspire future generations. This powerful, unified outpouring of belief in the value of scientific discovery and the pursuit of knowledge ultimately resonated deeply within the halls of power, leading Congress to reverse their decision. It was a testament to the idea that the pursuit of knowledge, the quest to understand our place in the cosmos, is not merely an academic exercise, but a deeply human endeavor that ignites passion and collective action. This moment underscored that Webb was not just NASA's project, it was humanity's project. The James Webb Space Telescope, therefore, is not merely a triumph of engineering and scientific ambition. It is a profound triumph of perseverance, international collaboration, and collective human will. It is the product of a monumental partnership between NASA, the U.S. Space Agency, the European Space Agency ESA, and the Canadian Space Agency CSA. This international cooperation spanning continents and cultures reflects the universal nature of the quest for knowledge, a recognition that the mysteries of the universe transcend borders and speak to the shared human spirit of inquiry. Its journey has been fraught with challenges. It has been delayed over 13 times, each delay a setback, yet each also an opportunity to refine, to improve, to perfect. Its project costs have increased from that initial modest $500 million to a staggering $9.7 billion, a sum that reflects the unprecedented nature of its capabilities and the sheer difficulty of building something so complex. But finally, after decades of waiting, of meticulous planning, of painstaking building, and of exhaustive testing, it is here. Its grand mission to peer into the heart of space and time, to uncover the mysteries of the formation of the first galaxies, stars, and planets, has at long last begun. You can be absolutely certain that when the James Webb Space Telescope finally launched from the European spaceport in Kourou, French Guiana, there were countless people across the globe, scientists, engineers, space enthusiasts, and dreamers, watching with bated breath, their hopes and anxieties suspended on every delicate maneuver. the moment of liftoff, the separation from the rocket, the first signal received from space. Each step was met with a collective sigh of relief and a surge of exhilaration. And you can also bet that now it's soaring through the silent void, its instruments meticulously cooling and aligning. Scientists from every corner of the globe are already fighting tooth and nail for the precious, highly contested time to get a chance to look through it, to be among the first to interpret its data, to discover what wonders it sees and what ancient secrets it unveils. Every second of observation time is incredibly valuable, a golden opportunity to touch the very edges of existence. So to all the countless teams involved with this incredible project, to the thousands of individuals who dedicated their lives to this dream, we extend our deepest gratitude and well wishes for the continued success of the deployment and the mission ahead. If it works, and by all indications its initial deployment has been a magnificent success, a testament to decades of meticulous planning and flawless execution, this instrument will be the biggest thing for space science, the most profound window into the cosmos for potentially decades to come. It is more powerful than any other space telescope we have ever conceived, including the venerable Hubble. It is so big with its tennis court-sized sunshield and its colossal golden mirror that it had to be folded up like a delicate piece of origami to fit onto the rocket that carried it into space. It is so precise and sensitive that it has to be kept at temperatures not much warmer than absolute zero to prevent its own internal heat radiation from getting in the way of its exquisite sensors. It is so expensive with its $10 billion price tag that it represents one of the largest scientific investments in human history. And it is so complicated with its 300+ potential single-point failures that its very functionality rested on a perfect ballet of unfolding in the cold vacuum of space. But now it is here. It is deployed. And it has an incredible mission ahead to study distant planetary systems for any subtle evidence of hospitable atmospheres that might hint at life, to understand the intricate formation of planets, stars, and galaxies themselves, and to peer out across the universe to objects so incredibly far away that the light they gave off has been traveling for almost as long as the universe is believed to have existed. In essence, the James Webb Space Telescope was built to spot the very first stars and galaxies, those ancient beacons at the very edge of our knowable universe, objects from the beginning of time itself. And already the first images have started coming in silent whispers from the cosmic dawn, proving the triumph of this audacious human endeavor. With the immense journey of its creation and deployment now a settled marvel, let us embark on the most anticipated leg of our cosmic voyage, a quiet contemplation of the initial discoveries and breathtaking images that the James Webb Space Telescope has already begun to send back to us. These are not just scientific data points. They are the universe's first whispers, ancient stories written in light, finally reaching our eager ears. Imagine, if you will, a priceless, intricately detailed tapestry woven through billions of years. Before Webb, we could only glimpse fragments of this tapestry, some parts clear, others shrouded in dust, or too distant to resolve. Now with Webb, it's as if a new, incredibly powerful light has been shone upon it, revealing colors and patterns we never knew existed, illuminating sections that were once mere shadows. The first images coming out of the James Webb Space Telescope are already promising to be spectacular, each one a testament to the power and precision of this engineering miracle. For those who have followed this cosmic saga, you know that the James Webb Space Telescope was first conceived in the 1990s, an audacious idea intended to cost only $1 billion and launch in 2007. However, numerous setbacks and delays plagued the project, pushing it back again and again. It was only in December 2021 that it finally launched, after years of tireless effort overcoming every hurdle. Since then, it has spent the intervening months slowly, meticulously unpacking itself, powering up its intricate systems, and testing its hardware in the cold, silent embrace of space. It is a 6,500 kilobar monster of precision, with a sun shield whose 14-21-meter dimensions are roughly the size of a tennis court. Its primary mirror for capturing light is 6 times larger by area than Hubble's lens, a colossal difference that allows it to pick up more photons from further away, creating incredibly crisp and detailed images. It boasts numerous cameras and scientific instruments, all designed to see across the infrared spectrum, a feature that is vital to its unique mission. As we gently explored earlier, due to the continuous expansion of the universe, all the light from the furthest reaches of space has been stretched or redshifted to the point that no matter what its original wavelength, it is now primarily infrared light. Therefore, the only way to truly see these ancient light sources, these faint echoes from the cosmic dawn, is with a powerful infrared telescope. On top of that, infrared light is much better at punching through dust clouds and other obscuring debris, giving the James Webb Space Telescope the incredible ability to see objects that were previously beyond the sight of Hubble. I often find myself comparing this magnificent telescope with Hubble, as the James Webb Space Telescope was originally intended to be Hubble's successor. However, given their slightly different fields of view, Hubble mostly sees in the visible and ultraviolet light spectrums, while the James Webb Space Telescope can almost exclusively see infrared and can't see some visible light spectrums at all. It's more accurate to say that the two telescopes complement each other rather than compete. They work together, forming a powerful duo, each extending the other's vision collectively, expanding our understanding of the universe in ways that neither could achieve alone. But that's not what truly captivates us right now. We are here to see what James Webb can do. So let's begin our journey close to home within our own galaxy, and then gradually expand our vision outwards, step by gentle step, towards the very edge of the knowable universe. You are in for some truly spectacular sights, cosmic revelations that defy imagination. Our first stop on this breathtaking journey is a place known simply as the Cosmic Cliffs, officially designated as NGC 3324. These magnificent structures are part of the vast Carina Nebula, located about 7,600 light-years away from us. When you gaze upon these cliffs in Webb's images, you are looking at truly massive formations, towering structures that are around 7 light-years high. To put that into perspective, the distance between our Sun and its nearest star, Proxima Centauri, is about 4.2 light-years. So these cosmic cliffs are immense, dwarfing anything we can imagine on Earth. What you see here is only a portion of the Carina Nebula as a whole. The actual nebula is much, much larger, sprawling across vast regions of space. It contains a hollowed-out center, a vast empty expanse within its heart, where the powerful stellar winds, streams of charged particles constantly blasted out by massive hot young stars, have swept away all nearby dust and gas, creating a colossal ethereal bubble. What we are witnessing in Webb's image is the very edge of this hollowed-out bubble, a dramatic boundary where fierce stellar winds meet dense cold clouds of cosmic dust. Scientists are immensely interested in this particular region of space. For one simple, profound reason: it helps answer fundamental questions about the formation of stars. Thanks to the relentless action of the stellar winds in this zone, the vast clouds of dust and matter are compressed and sculpted, creating dense pockets where matter can begin to conglomerate together. These dense pockets act as stellar nurseries, birthing places for new stars. It's like watching an invisible cosmic hand gather wisps of smoke and dust, gently squeezing them until, with a magnificent burst of light, a new sun ignites. However, for all our stargazing and our best theories, there are still many deep mysteries surrounding this process of star formation. How exactly do they form? What do the different stages of their embryonic development look like? It has historically been incredibly difficult to tell with clarity. Part of the challenge, paradoxically, is the very substance that is vital to the process, the dust itself. While essential for building new stars, this swirling cosmic dust also acts as a massive impediment to seeing the process happen clearly. It wraps around the forming stars, like a protective yet opaque cocoon, stopping scientists from seeing very clearly what is going on at the precise moments we would most like to observe. This is where the James Webb Space Telescope shines quite literally. Not only does Webb's image of the cosmic cliffs provide astonishingly more detail and clarity than any image captured by Hubble, but thanks to Webb's onboard AMIRI mid-infrared instrument, we can literally peel back the layers of dust and see what lies within. Imagine being able to see through a dense, dusty veil to observe the delicate, intricate process of a seed germinating. Webb's MIRI allows us to do just that for infant stars. Look at the clarity, the sheer amount of hidden detail revealed in the MIRI image compared to visible light. This unprecedented capability will provide scientists with invaluable data on the formation of stars for a long time, yet unraveling the secrets of stellar nurseries and helping us understand the very first steps in the lives of our cosmic siblings. So much for the birth of stars. Our next stop on this cosmic journey takes us to the other end of the stellar life cycle, uncovering more about the end of their lifespan. For this, let's look a little closer to home to NGC 3132, otherwise known as the Southern Ring Nebula. This particular celestial object presents a beautiful duality through Webb's eyes. The image on the left, taken by Webb's near-infrared camera NIRCam, shows the nebula in vibrant detail, while the one on the right, captured by MIRI, offers a profound, dust-piercing view. This breathtaking object is what astronomers call a planetary nebula. Although technically, that term is a bit of a misnomer, a charming relic from earlier times. While regular nebulas, like the Carina Nebula we just observed, are indeed the chaotic fertile birthplaces of stars, a planetary nebula is emphatically not a place where planets form. Instead, it was simply an unhelpful naming convention adopted by early astronomers who, with their less powerful telescopes, noted the often round disc-like shapes of these nebulas, and mistakenly thought they looked a bit like planets, hence the name. The name stuck, even though our understanding and interpretation of the cosmos have moved on considerably. Planetary nebulas like the Southern Ring Nebula are formed in a dramatic and beautiful celestial event, when a star, typically one with a mass similar to our Sun, reaches the very end of its long luminous life. Towards the twilight of its existence, the dying star sheds its outer layers, blasting vast quantities of dust and gas outwards into space. This expulsion creates the ethereal expanding shell that we observe as a planetary nebula. It's like watching an old star breathe its last, a magnificent final exhalation that paints the cosmos with its dying light. Knowing the chemical composition of this ejected dust and gas is incredibly useful for scientists. Understanding what materials exist in these stellar remnants helps us to understand what later waves of stars, planets, and even life itself might be made of. This cosmic recycling is fundamental to the universe's grand narrative. The elements forged in the hearts of stars and then expelled into space become the building blocks for subsequent generations of stars, planets, and everything else, including us. So once again, the James Webb Space Telescope's unparalleled ability to peel back the layers of dust to see what lies within is invaluable. Compare this with Hubble's image of the Southern Ring Nebula to truly grasp the sense of increased detail that James Webb is able to bring to bear. Hubble's view, while beautiful, appears almost like a faded photograph next to Webb's crisp, almost three-dimensional rendering. From these new detailed observations, scientists have made fascinating discoveries. For instance, they have learned that the second star within the system, most planetary nebulas, are formed by binary star systems where two stars orbit each other, still has not actually exploded. This means the formation of its own planetary nebula is still likely to come in the distant cosmic future. We can also get a much better sense of how the powerful gravitational interactions of these two stars stir the nebula. Mixing the dust and gas together in fascinating, intricate patterns, painting swirling masterpieces of dying light and newly forged elements. It's a profound testament to the cyclical nature of the cosmos, where endings give way to new beginnings. Now let's look a little further out beyond the familiar confines of our own Milky Way galaxy and expand our gaze to the neighboring Magellanic Clouds, those smaller satellite galaxies that dance around our own. If we want to continue our exploration of star creation, it makes perfect sense to find a location that is actively, spectacularly creating them. Approximately 161,000 light-years away from us lies the Tarantula Nebula. This awe-inspiring celestial region is so named because to the imaginative eye it evokes the idea of a giant tarantula lurking within its silken web, its long glowing filaments resembling the creature's hairy legs. Aside from its obvious otherworldly beauty, this area is of particular note to scientists because of its remarkable similarity to a crucial period in the universe's history, known as the Cosmic Noon. The Cosmic Noon, to our best current understanding, was a highly energetic and incredibly prolific period that took place roughly 1 billion years after the universe began. During this epoch, star and galaxy creation was at its absolute most prolific. It was a time of immense cosmic fireworks, a period when the universe was literally brimming with the birth of new suns and the coalescing of vast stellar cities. Scientists theorize that the conditions within the Tarantula Nebula, its density, its chemical composition, the sheer rate of star formation, would have looked something remarkably like this primordial era. It's like having a living, breathing fossil from a foundational period of cosmic history right in our galactic backyard. The James Webb Space Telescope has been able to spot stars here that are only just coming into being, still shrouded in their dusty cocoons, in a fascinating period of time to study. Webb's unparalleled infrared vision cuts through the thick dust of the Tarantula Nebula, revealing thousands of previously unseen young stars and even some still-forming protostars, tiny embryonic suns barely flickering into existence. This direct observation provides an invaluable opportunity to understand the processes that dominated the universe's early years, to see the blueprints of how the first galaxies were assembled and how stars ignited in an environment very different from our current, more settled cosmos. The Tarantula Nebula, viewed through Webb's eyes, becomes a dynamic living laboratory for cosmic history, a place where we can witness almost in real time the echoes of the universe's vibrant youth. Let's look further out again, stretching our cosmic gaze even wider. As our view extends across truly intergalactic distances, we begin to lose track of individual stars. They become too small, too dim, too countless to resolve individually. Instead, we start seeing things on a truly galactic scale where entire cities of stars dance across the cosmic stage. Even here in these unimaginable expanses, there are beautiful slow-motion ballets being played out, magnificent gravitational interactions that unfold over millions and billions of years. Our next stop is a famous formation known as Stephan's Quintet. This is a visually striking group that appears to be a formation of 5 galaxies, famously featured in the classic film It's a Wonderful Life. However, a fascinating detail reveals that one of these 5 is not truly next to the others in space, but just happens to look that way from our perspective, a trick of cosmic alignment. It's a reminder that what we perceive is often just a 2-dimensional projection of a complex, 3-dimensional reality. The truly captivating aspect of Stephan's Quintet for astronomers is the profound interaction occurring between the other 4 galaxies. It is thought that these 4 galaxies will one day collide and merge, a grand cosmic fusion that reshapes their very identities. Indeed, 2 of them, the central pair, are already engaged in a magnificent, violent gravitational dance, slowly, inexorably spiraling into each other. The James Webb Space Telescope allows us to see clearly the brilliantly hot dust and gas being kicked off as these 2 central galaxies circle each other. These aren't mere gentle swirls. The gravitational forces here are mind-bogglingly intense, the energy profoundly immense. It's a chaotic, yet beautiful dance of cosmic destruction and eventual creation, a violent embrace that will ultimately forge a single, larger galaxy. This is a dance that is truly only appreciable at such vast galactic scales, a slow-motion collision unfolding over hundreds of millions of years. Webb's image of Stephan's quintet is not a single snapshot taken at one precise moment. Instead, it is a magnificent composition of almost 1,000 separate images that James Webb meticulously took, which scientists then painstakingly stitched together. This multi-exposure approach gives the final composite image incredible resolution, allowing for the picking out of astonishingly fine details, revealing the intricate tendrils of gas and dust being torn and stretched between the interacting galaxies. It's like a cosmic mosaic, each tiny tile contributing to a grand, breathtaking panorama of galactic interaction, providing an unprecedented view of how galaxies evolve through mergers and collisions. Now let's push our cosmic gaze even further out to the absolute limits of Webb's vision, until even this extraordinary instrument is straining to see. We arrive at an image known simply as Webb's first deep field. This image is taken from an area of the night sky so incredibly small, so infinitesimally tiny that if you were to hold a single grain of sand at arm's length, it would completely block this patch of sky from your view. Yet within this minuscule cosmic window, Webb has revealed a universe teeming with ancient light. At this unimaginable scale, individual stars are almost completely absent. They would be far too small and too dim to detect on their own at such distances. Most of what you can perceive here are not stars, but galaxies, countless shimmering islands of stars, each one a universe unto itself. Here, you can clearly discern the fascinating gravitational lensing effects being created by relatively nearer objects. These massive foreground galaxies, with their immense gravity, subtly bend and magnify the light from the even more distant galaxies lying behind them, much like a giant cosmic magnifying glass. This bending distorts the light, stretching and smearing the images of what lies beyond, creating a beautiful fish lens effect that is both a visual spectacle and a powerful tool for cosmologists. In this single tiny patch of sky, Webb has begun to reveal the very edges of the universe. And nestled within this awe-inspiring panorama in this one single image is one of the oldest galaxies we have ever sighted. It is so incredibly far away, so profoundly ancient, that the light from it, when it was born at the very beginning of the universe, has only just now, after a journey of billions of years, finally reached our detectors. But where is it? How do we find this ancient beacon among the countless other galaxies? We are going to need to zoom in to focus our attention on the faintest whisper. Do you see it? It is admittedly quite small, a tiny reddish smudge almost lost among the brighter, more structured galaxies. But this tiny dot holds an immense secret. By meticulously evaluating specific markers within the light given off by this tiny red galaxy, specifically by analyzing its redshift, scientists are able to identify precisely how far it is and thus how long the light from it has been traveling. By comparing its deeply redshifted light to the normal unshifted visible light from similar sources, which we can observe from closer galaxies, this tiny dot was found to be an astonishing 13.1 billion light-years away. Given that the universe is currently thought to be approximately 13.8 billion years old, this is truly one of the earliest galaxies that we will ever be able to see. It is a direct glimpse into the universe when it was barely a few 100 million years old, a mere infant in its grand cosmic timeline. Now you might be a little disappointed by how small and indistinct this ancient galaxy appears. After all the hype, all the advanced technology, it's just a tiny dot. However, there is immense room for hope and even more profound awe. Compare this image with one taken by Hubble of the exact same region of sky. Obviously, James Webb's image is undeniably crisper and clearer, revealing more detail and showing far more objects that were previously invisible. But there is one vital, truly astonishing distinction between these two images. Hubble, for its deep field image, took its image by patiently staring at this patch of sky for 10 days, slowly gathering every single photon it could from this region of space and painstakingly compiling them into a single composite image. It was a Herculean effort of light collection. James Webb, on the other hand, took only half a day, a mere 12 hours, to capture its own superior image of the same region. What this profound difference in observation time implies is truly mind-boggling. If James Webb was able to take such a detailed, clearer image in just 1/20th of the time that Hubble required, imagine how incredibly detailed and profound an image it could capture if it were given a comparable amount of time, say 10 days or even more. In other words, this tiny, seemingly unassuming dot is likely not the best that James Webb can do. It is just the beginning. It is a tantalizing hint of the much deeper, much richer secrets that lie hidden within the cosmic darkness, waiting for Webb's patient gaze to unveil them. I sincerely hope these initial images and the stories they tell have given you a profound sense of the scientific breakthroughs possible with the James Webb Space Telescope. But beyond the science, I hope they have also reminded you just how incredibly beautiful, how utterly breathtaking the sights of the universe truly are. Images like these to me are not just data. They are cosmic poetry, visual symphonies that blow the mind and stir the soul. Sadly, we are going to have to be a little patient to see what further, even more astonishing discoveries James Webb might have in store for us. Webb has only just finished running through its initial calibrations, letting its instruments cool off to their extreme operational temperatures, and meticulously making sure everything is working perfectly. The scientific community is buzzing with anticipation. There are already long, hotly contested queues of scientists from around the world, literally fighting tooth and nail over who gets to use this precious instrument to do what over the next 5 to 10 years of its expected lifespan. Each second of observation time is hotly contested, a golden opportunity that could define careers and reshape our understanding of the universe. Webb will be investigating distant exoplanets for subtle signs of hospitable atmospheres that might hint at the presence of life. It will continue unveiling dusty nebulae to find the hidden origins of stars and planetary systems. It will help us to understand the fundamental differences between an old mature galaxy like our own Milky Way and the young chaotic galaxies that formed just after the Big Bang. With a tool as powerful and versatile as the James Webb Space Telescope, truly, who knows what else we are about to discover? The universe holds countless secrets, and Webb is poised to be our most effective key to unlocking them. The James Webb Space Telescope has now been in space for over a year, a silent sentinel, gazing into the cosmic depths. The images it continues to capture are truly captivating with their breathtaking beauty and astonishing high-resolution detail. But as we delve deeper into the universe's secrets, it's often what Webb doesn't see that allows us to truly shine a light on the universe's inner workings. This concept of seeing without seeing might sound strange, even paradoxical, but it is a fundamental foundation upon which much of modern astronomical observation is based. Through clever techniques, it allows us to understand the intricate chemical composition of molecular clouds in nebulae, to decode the mysterious makeup of atmospheres around distant exoplanets, and even to confirm the existence of delicate rings around tiny asteroids in our own solar system. The James Webb Space Telescope, with its unprecedented sensitivity and precision, is uniquely placed to take advantage of these subtle yet incredibly powerful observational methods. Imagine, if you were listening to a conversation through a closed door. You can't see the speakers, but by carefully listening to the pauses, the inflections, the missing sounds, you can begin to piece together what is being said. In a similar vein, the universe often reveals its deepest secrets, not through blinding light, but through the subtle absorption or absence of it. In this next part of our journey, we will explore the awesome power of not seeing as well as seeing. in helping us expand our understanding of the vast, mysterious space around us. Let's begin with an image of NGC 346, a mesmerizing cluster of stars nestled within an associated nebula found in the Small Magellanic Cloud, approximately 210,000 light-years away from us. NGC 346 is particularly interesting to scientists because the conditions and the relative abundance of metals found in this area are remarkably similar to the conditions that existed roughly 2 billion years after the Big Bang, during a highly energetic period of the universe's history known as the cosmic noon. At that pivotal point in cosmic time, countless stars and galaxies were rapidly forming an era of intense cosmic creation. By studying this nearby modern contemporary of the cosmic noon, scientists can gain an invaluable, clearer idea of what that ancient formative period might have been like. It's like finding a living fossil from a bygone era, allowing us to touch the past in the present. But how do scientists precisely know the metallic composition of these beautiful swirling tendrils of stellar matter? One elegant method is through analyzing emission lines. When gases get incredibly hot, perhaps because they have been warmed and energized by the intense radiation from nearby powerful stars, the atoms that make up those gases become excited. In their natural tendency to return to a lower energy state, these excited atoms seek to dissipate that excess heat and energy by emitting radiation, specifically light. However, for reasons rooted deep in the intricate world of quantum mechanics, which we won't dive into tonight, every atom can only emit radiation at a very specific, unique wavelength. This remarkable property means that each element in the universe possesses a distinct chemical fingerprint in the light it emits. If you know the precise wavelengths of light given off by, say, superheated oxygen, you can always tell with certainty when oxygen is the source of any light you come across. So by precisely measuring this emitted light, the James Webb Space Telescope gains an invaluable insight into the chemical composition of this nebula. Webb is particularly suited to investigating nebulae like NGC 346 because its infrared vision is much more able to pierce through dust clouds and see what lies at their hearts, observing the light emitted by the very hot energized gases within. Webb's superior sensitivity, a result of its enormous light-gathering mirror and highly advanced detectors, allows it to detect intricate details that had never been seen here before. This includes identifying small nascent disks of dust that were forming around developing protostars, tiny embryonic suns, potentially even marking the very beginnings of new planets. This direct observation of such fine details allows scientists to witness almost in real time the building blocks of new stellar systems taking shape within these cosmic nurseries. These are standard, yet incredibly powerful methods of observation, providing a wealth of information. However, I started this segment by talking about seeing through not seeing, and when it comes to astronomy, merely looking at the light emitted by objects is often not enough. Sometimes the most profound revelations come from understanding what light isn't there. For instance, recently, Webb imaged something quite different, an ice cloud. More specifically, it is the Chameleon Dark Molecular Cloud, another vast, cold birthplace of stars. As you can imagine, an ice cloud is far too cold to radiate light with distinct emission lines. Its atoms are not sufficiently energized to glow brightly. So here, scientists need to use a completely different technique to learn its precise chemical composition. But thanks to Webb's piercing infrared vision, a different, equally powerful method can be employed, one that relies on the very principle of seeing through not seeing. As I said earlier, when atoms become excited, they release radiation light. But this process also works elegantly in reverse. When atoms are hit by radiation light, they can absorb that energy and become excited themselves, becoming a little warmer in the process. This fundamental principle has a clever implication. If you shine a continuous spectrum of light through a gas cloud and then carefully measure which frequencies or wavelengths of light get blocked or absorbed by that cloud, it will tell you just as certainly what elements make up that cloud, as if you'd heated them up and they were radiating their own light. This is what I mean by seeing through not seeing. The missing light provides the crucial information. Of course, this technique hinges on there being a source of continuous light shining through the cloud you want to look at. Fortunately, in the universe, this often occurs naturally through all the countless stars sending out light from behind objects, like the chameleon Hubble dark cloud. The light given off by stars is much more varied in its wavelength than the light given off by specific gases, because solid objects, like the hot cores of stars, emit photons under different physical rules than diffuse gases. This provides a smooth, continuous background light source against which scientists can check for the precise absorption lines, the missing frequencies that reveal the cloud's composition. There has always been a significant problem, however. With applying this technique to objects as large and dense as a molecular cloud, they can be too opaque, too thick, for starlight to be able to penetrate sufficiently. It's like trying to shine a flashlight through a very thick dark wall. This is precisely where the unprecedented power and sensitivity of Webb truly come into play. Thanks to Webb's unparalleled ability to gather even the faintest whispers of infrared light, for the very first time, scientists have been able to detect the light from distant background stars through the incredibly thick, dense cloud of chameleon nightmares. This breakthrough observation allowed them to meticulously analyze its chemical composition through the absorption lines, and what they found was nothing short of a surprise, a profound revelation. Not only does the chameleon dark cloud contain significant amounts of water ice, but it also harbors some of the fundamental building blocks of life, complex organic molecules, such as ammonia, methane, and methanol. This means that any stars and planets that one day form within this frigid, icy cloud will begin their existence with some remarkably complex chemicals already present, giving the ball a significant head start. And if this turns out to be a common phenomenon throughout the universe, if these complex building blocks are widespread in stellar nurseries, it makes it much more likely that worlds capable of bearing life are actually widespread throughout the universe, significantly decreasing the likelihood that we are alone in this vast cosmic ocean. It's a message of hope whispered from the heart of an ice cloud. Spectroscopy. The science of studying the chemical makeup of objects from their absorption and emission lines is a remarkably versatile tool, and its applications extend to much more than just molecular clouds or nebulae. Through it, we can also learn a profound amount about the atmospheres of exoplanets, worlds orbiting stars beyond our own sun. Webb was able to make a truly groundbreaking discovery regarding the chemical makeup of one such exoplanet, JWST P39b. This is a gas giant, a Jupiter-sized exoplanet, located approximately 700 light-years away from us. The ingenious method used was to wait until JWST 39b passed directly in front of its own star from Webb's perspective. As the exoplanet transited, a sliver of light from its parent star filtered through the planet's atmosphere. As this starlight passed through the atmosphere, the gases within would absorb light at certain specific frequencies, leaving their distinct chemical fingerprints on what remained of the starlight. By meticulously analyzing these subtle changes in the star's light, Webb detected sulfur dioxide in JWST 39b's atmosphere. This was a monumental first, the first time this particular compound had ever been definitively seen in an atmosphere outside of our own solar system. This discovery alone hinted at complex photochemistry occurring in the exoplanet's upper atmosphere processes driven by the intense radiation from its star. Furthermore, Webb also provided a remarkably complete breakdown of all other chemicals and elements present in JWST 39b's atmosphere, including some clear evidence of water vapor. Such detailed atmospheric profiles are crucial steps towards identifying potentially habitable worlds, allowing us to gauge their environmental conditions. As impressive and revealing as spectroscopy is, it is not the only way Webb makes profound discoveries by not seeing. There is a second equally elegant process known as occultation. that astronomers have been making use of over the last century. Rather than searching for the spectroscopic breakdown of light from stars watching for occultation, involves meticulously noting a star's brightness over time. By looking out for the sudden brief dimming of a distant star's light, scientists can discern the presence and even some characteristics of dark, otherwise invisible objects that pass directly in front of them. It's like knowing something is there because it casts a shadow. And the James Webb Space Telescope, with its unparalleled precision and continuous monitoring capabilities, is exceptionally good at spotting such fleeting dimming moments. Within our own solar system, in the intriguing region between the orbits of Saturn and Uranus, there lies a rather unusual asteroid called Chariklo. It is a relatively small body, about 250 kilometers, approximately 155 miles in diameter, and it's the largest of the asteroids, known as the Centaurs, a unique class of icy minor planets that tend to orbit between Jupiter and Neptune. However, its size is not its primary claim to fame. Chariklo is impressive because in 2013, it was discovered to be one of only 5 objects in our entire solar system, besides the gas giants, known to possess rings. For a while, scientists did not think that objects as small as Chariklo could actually support stable rings. The gravitational pull seemed insufficient to hold such delicate structures together. Even now, they are unsure whether these rings are relatively young, perhaps having formed only in the last few million years from a recent collision, or whether some mysterious gravitational phenomenon, perhaps involving tiny shepherd moons that we haven't yet seen, is keeping them in place. The James Webb Space Telescope tested its formidable ability to observe occultation by attempting to spot these very rings as Chariklo passed directly in front of a distant background star. This was no easy task. It takes extremely precise predictions to know exactly where Chariklo would orbit and which specific star to watch. Given the immense distances and the tiny sizes of such objects in space, even the smallest miscalculation in timing or position would result in no occultation being observed. The target star would simply continue to shine brightly oblivious to the hidden celestial ballet. That said, Webb, with its unparalleled accuracy, was indeed able to spot Chariklo and its 2 delicate rings as they passed in front of the star. It meticulously noted the occultation, the sudden dip in brightness of the asteroid itself, as well as 2 distinct brief dimmings caused by each of the rings as seen in the meticulously collected light curve data. The rings themselves were far too small to be imaged by Webb directly, even with its incredible resolution. But from the precise timing and duration of the sudden dimming in the star's brightness, Webb was able to clearly make out the existence and characteristics of the rings, which are thought to orbit about 400 kilometers from Chariklo itself. The larger of the rings is only 6.9 kilometers wide, and the smaller one is an astonishingly tiny 120 meters wide. These are truly delicate ethereal structures. It is not yet entirely clear what these rings are made of, but Webb was able to detect crystalline water ice on the main body of Chariklo, hinting at the icy nature of this small, mysterious world. With further observations, more information about these elusive rings will undoubtedly come to light, helping us understand the surprising prevalence of ring systems in our solar system. And speaking of rings, there is one more image, one more profound cosmic story I want to share with you, a sight that I personally found utterly spectacular. These are the strange reddish-purple rings of Wolf-Rayet 140 WR1 These rings are unlike anything I have ever seen in space before. When the astronomers first encountered them, their initial thought was that something might be wrong with their equipment, that it was a glitch or an artifact. The rings seemed more like the ripples in a placid pool after a stone has been dropped, or the concentric growth rings of an ancient tree, rather than an actual interstellar object. And yet these magnificent glowing rings actually represent over 100 years of a truly incredible, repeating cosmic phenomenon. At the very heart of these rings lies not one star, but a binary star system. two massive luminous stars orbiting each other in a tightly choreographed cosmic dance. Every 8 years, like clockwork, these two stars at the center of the system complete one full orbit and approach closest to each other. During this close pass, their powerful stellar winds, streams of charged particles constantly being blown away from their surfaces, interact violently. This intense interaction acts like a cosmic snowplow, compressing and blowing a fresh, expanding ring of dust and gas outward into space, creating a new ethereal circle. What Webb observed was astonishing. There are at least 17 distinct rings, meaning this process has been going on consistently every 8 years for the last 130 years or so. This phenomenon is vast. The furthest ring is an incredible 70,000 times the distance from the Earth to the Sun, an almost unimaginable scale. The level of detail Webb was able to capture is truly incredible. Previous fuzzier glimpses at this system had only indicated that there might have been one barely discernible ring, incredibly blurry compared to the pristine resolution captured by Webb. These distinct, well-defined rings were incredibly useful for astronomers. They provided a unique opportunity to spatially document the chemical compositions of the rings of Wolf-Rayet 140, over time essentially creating a historical record of the system's chemical output. Through meticulous analysis of these glowing probes, scientists found compelling evidence for what they believed to be polycyclic aromatic hydrocarbons, PAAs. PAAs are complex organic molecules, often called soot, that have been known for a long time. They are crucial components in the formation of stars and planets, acting as building blocks and cooling agents in cosmic clouds. However, their precise origin has long been a profound mystery. Now, thanks to this groundbreaking discovery by the James Webb Space Telescope, the Wolf-Rayet binary stars have stepped forward as one possible source for this crucial compound. It suggests that these powerful interacting stellar systems could be cosmic factories churning out the very organic molecules necessary for the next generation of stars and planets. And this entire profound discovery was only possible because of the exquisite spectroscopy capabilities of James Webb and its unparalleled ability to see and crucially not see light in such incredible detail, allowing the hidden chemical fingerprints to be revealed. There will undoubtedly be many, many more such profound discoveries that Webb will make in the years to come. Such a powerful telescope can capture images at far greater clarity than any space telescope before it. But I thought it was important to emphasize tonight that not all of Webb's biggest breakthroughs are stunning visual images painting the night sky. Many of its most significant revelations lie in the tiny hidden details and the subtle nuances of things not seen. Light not appearing when it might be expected, to indicating the precise presence of hidden chemicals or previously unobserved celestial objects. Because it turns out it's not always about what you see. Sometimes what you don't see is the most informative, the most profound, the most revealing. It is in these quiet, subtle observations that the universe whispers its deepest, most fundamental truths. As you drift to sleep, consider the silent, unseen processes that shape our cosmos and how our newest eye is now attuned to their every subtle echo.